ce jour-là.
Like this.
You prefer the stick or the phone?
The stick. I'm old school in some sense. I prefer physical things. Yeah. Okay. Do you hear me?
Yeah, it's important that they will hear you for sure.
Okay.
So Sasha is going to talk about young solar wind clearing structures from inertial to subanis range. So you are
Yeah.
15 minutes, 3 minutes I will give you.
Okay. So, good morning, everyone. I would like to give a talk on the solar wind coherent structures using multi-scale approach. So, coherent structures are really important part of the solar wind turbulence because uh, they are they correlate with the regions of increased heating in the solar wind, which was shown by numerous papers like Osman and others. And we can define coherent structures as high amplitude, stable for the times of nonlinear, in comparison to the nonlinear time, and localized in space events. And here you can see a classical result that if you detect coherent, if you assume that high PVI values correspond to coherent structures, which is one of the methods to detect them, then you can find the correlation between high PVI areas and higher ion temperature in the solar wind. So this is the manifestation of the fact that coherent structures can be important for the heating. Yeah, in order to investigate coherent structures, we use Parquet solar probe data, and it was on the first perihelion. In this blue region we show here, yeah, at the distance of 0.17 astronomical unit. Yeah, so we are going to, I would like to show you the coherent structures that we detected and compare them with the models. So here you can see in orange you can see the total spectrum of magnetic field, and you see in red region this is the inertial range. In green you can see the band which corresponds to ion kinetic scales, and in blue blue region corresponds to the frequencies that are corresponding to subion scales if we assume Taylor hypothesis. And if we filter the magnetic field using Hamming filter, we at the scales, if you use a low pass filter at the scales more than 100 seconds, and if you compare the original magnetic field measurements from the Parquet solar probe with the synthetic signal, which has the same spectrum as measurements but random phases, then you would observe that both at the larger scales, the distribution is almost the same, and it is almost Gaussian. Whereas if you consider the data on inertial range, you will have non-Gaussian tails, but for the synthetic signal which has random phases, it follows Gaussian distribution. And the smaller the scale is, here it is shown for the subion scales, the more is the probability of the more is the non-Gaussian tails of the distribution of the fluctuations. So those non-Gaussian tails, they are corresponding to the coherent structures. So how we detect structures? There is a well-known method which is PVI, but we apply another one which is called the local intermittency measure. So it is based on the Morley wavelet transform of the magnetic field. If you consider the time interval of 30 minutes shown here with radial tangential normal magnetic field components, and then you calculate wavelet transform of this field, and normalize it to the average L energy at the given scale. Then you get a local intermittency measure, which is the function of time and scale. Total, it means that I consider all three components of the field. And it is shown here. So one can see numerous vertical lines that correspond to coherent structures as far as they show couple phases across the scales. And if you compare the real measured signal by the Parker-Solar probe with a random phased signal, you will not observe any of those vertical lines that correspond to coherent structures. So our method of detection is the following. We would like to find, so we compare the local intermittency measure of the original signal with the maximum value of the local intermittency measure for the synthetic signal, which gives me the threshold to detect the structures. So now I would like to show you the 4 examples of structures that we analyzed. First, let me introduce the format of the figure. So here you can see the magnetic field data, raw data, during the period of plus minus 100 seconds around the center of the structure. Here you can see the hodograph of the magnetic field in the the magnetic field is transformed into a minimum variance reference frame, and you can see the almost linear hodograph. Here we compare the increment the normalized magnetic fluctuations with the substituted mean value, with normalized by the B0, with the velocity measurements normalized by alpha and speed. And in this case, this discontinuity, you can see the correlation in jump of the magnetic field and velocity, but the amplitude is not the same. So yeah, and here you can see the zoom of the modulus of the magnetic field. You can see that the strength of magnetic field changes across the sheet, and we can see some decrease in density and almost constant temperature of ions and protons. Then what we would like to do is to look at the filtered magnetic field fluctuations. So here is the filtered magnetic field fluctuations at the same time period, plus minus 100 seconds. So this is fluctuations in inertial range, which is essentially the same as this current sheet, but as far as it is a bandpass filter, it has a bit different form. You still keep the linear polarization here, but if you look at the smaller scales, this panel corresponds to ion scales fluctuations within the center of this current sheet. You can observe the vortex-like fluctuation with the different hodograph, and at subion scales, if you consider fluctuations at subion scales, it is shown here on the smaller time range. You can see the structure, which amplitude is much higher than the standard deviation of the fluctuations during the 5 hours interval, which is shown in gray. Maybe it's not well seen here, but the standard deviation of the fluctuations at these scales, at subion scales, is shown in gray here. So the amplitude of the subion scale structure is much higher than standard deviation. So what can we conclude? That within the current sheet, we observe some intense fluctuations that are possibly corresponding to embedded structures within this larger current sheet. Yeah, and what is also interesting is that in the dashed line, I show the compressible part of magnetic fluctuations. I mean um, the longitudinal and the ratio of the amplitude of the structure and the parallel component of the magnetic field fluctuation is about 1/2. So this structure is quite compressible. Yeah, so this is the second event. This is also a current sheet, but instead of linear polarization as it was shown in the first case, this one has arc-like polarization. This one is much more alphabenic. I mean that the jump in magnetic field and in velocity, they correspond quite well. And what is interesting is that this current sheet is embedded into the much larger much larger volume where the magnetic field is decreased. Here is the zoom in black. So the magnetic field decreases at the large scale, at the scale of about 100 seconds, and the current sheet thickness is much smaller. Yeah, so within this current sheet, we observe at the ion scales, we observe some peaks in that have a circular hologram in the plane perpendicular to B0. And on sub-ion scales, we once again observe very intense structure, and the gray region is very tiny here. So it means that this structure is really intense in comparison to the average level of the fluctuation and this scale during the 5 hours time interval. Yeah, this is the third example. At the if you look at the first panel, this is the raw data, and you can see in yellow this is a fit of a large scale fit, I would say, and you see that it changes sign. So and at the same time, the magnetic field within the inner part of the current sheet, it fluctuates really strongly, and at the same time, those fluctuations are very alphenic. As you see, magnetic field and the velocity, they correlate simultaneously, and the correlation coefficient is very high. Yeah, I will try to make it faster. So once again, we observe embedded sub-ion ion scale and sub-ion scale structures, and those fluctuations, if we filter out the current sheet, we get this fluctuation, and this resembles very much the crossing of the alpha vortex. So interpretation of this event is possible. One of the possible interpretation of this event is embedded alpha vortex inside the current sheet. So the last event I'm going to show is, yeah, it has multiple changes in multiple it is a sequence of current sheets in the plane perpendicular to the background magnetic field. This structure, yeah, and within once again you can observe sub-ion scale structure within the very center of this large scale event. Why do we see these quasi-periodic fluctuations? We still need to make some analytical work on it. And what is also, if you are interested in the number of structures at different scales, so here, so the smaller scales are here, the larger scales are here. This is the number of events. So if you try to detect coherent structure scale by scale at the given using local intermittency measure, at each scale from largest ones to the smaller ones. And here is ion kinetic scales. You will observe the 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 uniform dependence of the number of events as a function of scale. So there are much more smaller structures. Smaller scale structures are much more numerous. But if you compute the volume that they occupy, then you will observe that it decay in the inertial range and then saturates at starting at ion kinetic scales. We still need to think about this. Yeah, and the last thing we are going to do is that what we are going to do is compare our collected statistics, which is a quite large one, with simulations of the crossings of different types of structures, such as monopole affine vortex, shown here, dipole, affine vortex, rotational discontinuity, and magnetic hole. All those structures, they were reported, they were observed in the solar wind, and they have distinguishing properties, which is if you cross it along the set of the trajectories shown in blue cone, then you get a distribution of the, and for each trajectory you calculate minimum variance eigenvalue ratios. Then you will get different distributions for different types of structures. And this can be possibly a distinguishing feature, how we can say statistically if at one scale or another scale, one or another type of structure dominate. So this is my conclusion. We investigated solar wind coherent structures at multiple scales, from MHD scales down to subion scales. We showed a number of examples, and they show that numerous subion scales are usually embedded into the larger ones. Yeah, small scale structures are more numerous, but they occupy less space. Yeah, and the future work is to compare the statistics of observed structures with models to be able to say something about dominant type.
Okay,
Yeah,
thank you. You already have Bill.
Very nice presentation. I have a comment and a question. The comment is that I guess your filling factor analysis can be recast as a scale-dependent kurtosis, which would be interesting to do.
Yeah.
And the other thing is, okay, so you see that these structures that you're seeing.
Yeah. So
okay.
You can observe the kurtosis of the three components of magnetic field using increments, and it grows till the ion scales, and then it saturates, I would say.
Okay, good.
But
so,
yeah, but
okay, so I withdraw my comment in that case.
Sorry.
What's that?
Yeah, this is kurtosis calculated from wavelet coefficients, and this is different because you can see that it grows even on subion scales, and
So
I'm not sure about interpretation, but possibly this is because at subion scales we do not observe a lot of current sheets, but more vortex-like events, maybe, and that's why maybe wavelet detects them in a different manner in comparison to the increments.
So
But
the bottom
I'm
one
not
is
sure
the increments. The bottom one is the increments.
This one is amplitude of the wavelet coefficient.
Wavelet.
Yeah.
And what's the bottom one?
The bottom one is increments between the field at the scale tau. So.
Okay.
Yeah.
Okay. Well, anyway, that raises other questions, but
yeah.
I have my question now, right?
You want to ask your question?
Well, I had that was my comment, but but I didn't know that they already did it. But the answer to the comment raises other questions. But let's wait on those. My question was, you identify these structures and you've seen that they are alphanically aligned in the sense of the relaxation that Chicho Pekara talked about yesterday. I mean, almost all MHD directionally and aligns. But how about the rest of it? How about the quasi-force-free, Beltrami, pressure balanced? I mean, are these structures partially relaxed in all senses of partial relaxation or only alphanic? Because all of these things reduce nonlinearities, right?
Yeah, yeah.
And it seems to me that they look, from the hodograms, they look like they might be almost force-free. But I'm wondering if you've analyzed those in that way. Or maybe you should.
Yeah, I agree. Thank you for the comment. I need to do this.
Sorry, funziona. Okay, I have questions. The first one is, if I correctly understood, the kurtosis you have computed in the previous figure, in the upper panel, this is done scale by scale in terms of wavelets.
In terms of wavelets, yeah, so I compute wavelet transform,
Okay.
and then at the given scale, I have my wavelet coefficient,
Okay,
and
yeah.
I compute.
This is not kurtosis at all. This is not kurtosis at all. Looks at a fresh book. No. Because kurtosis in turbulence is a filter for frequencies higher than a fixed one. So this is the reason why you use increments. Okay. So you have to filter the other one. Want to compare with increments. Otherwise, you got differences in these two. This is just. Second one is just. From one scale to the smaller one.
Yeah.
You cannot compute to a single scale, because this means that you are computing the kurtosis of the fluctuations at that scale. But this is not the kurtosis as the one that is defined in turbulence. You have to take care about these things. Yeah, exactly. It's a kurtosis density.
Okay, thank you.
Is that have you tried to see how much your results depend on the choice of the wavelet? Sometimes I observe some figure that reminds very well of Morlet one. So this is something that you perhaps, there are methods based on empirical methods, like for instance empirical mode decomposition or other methods that can be used in order to have not so many scales and at the same time to have more information about this. This is just a suggestion.
Okay, thank you.
But what Sasha shows here, physical time.
Yes, but wavelength, they are inherently.
They find the time where we look at this.
Many situations. You have to take care of these things. So just a suggestion. I use wavelength too. So sometimes I have problems with
The work that Denise done in Solar Wind, we found everything with this wavelets, and current rates, and solid zones, and vortices.
Yes, I'm sure that
for me, it was like a test of this other
I'm
one.
sure that you can identify singularities in the signal, because essentially you can identify singularities with this method. Local intermittency measure was introduced by Farmer in 1992 to identify singularities in turbulence, essentially, and just to extract these singularities to see which kind of structure they are. This is just a suggestion. It's just a suggestion. Nothing more.
There will be a desk outside in coffee break where I put a wavelet discussion, and you can continue there. Okay, so let's thank the speaker again, and welcome the next one. Okay, we have Mirko Stumpo, who is going to talk about semi-empirical Langevin models for solar wind magnetic field fluctuations from MHD to subion scales.
Okay, thank you. Good morning to everyone. Just to introduce myself, I am Mirko Stumpo. I am a PhD student under the supervision of Giuseppe Consolini. Okay, so the aim of my presentation is to investigate a Langevin-like approach as a framework to describe solar wind magnetic field fluctuations in the high frequency range by using Parker solar probe data. The advantage of this method, I mean the Langevin processes method, is that Langevin processes have a thermodynamic interpretation and allow to describe far from equilibrium fluctuations through the definition, for example, of an entropy production based on the single realization of the process. This entropy production also satisfies a fluctuation theorem, and in particular the dynamics in this framework is modeled as a stochastic process, and the model is computed with respect to the dynamical scales, not with respect to the time. Okay, as I mentioned, we model the dynamics in scale as a stochastic process. But this means that we have essentially the usual Richardson picture in this framework. We have structures essentially at all. Il pointer. Okay. Sorry. We have essentially structures at all scales, and the fluctuations of the magnetic field follow essentially a stochastic path of a trajectory in this space filled by these structures. And these paths are generated by the Langevin equation. And in this framework, I mean the Langevin equation represents the equation of motion of the fluctuations in this space. Mathematically, we have the process at fixed spatial scale defined as the increments of the magnetic field with respect to the time variable, but we can recast the time variable into the spatial variable by using the Taylor hypothesis as usual. And in this case, we have this signal at fixed spatial scale, and the evolution of these fluctuations across the dynamical scales is expressed by this stochastic differential equation, where the coefficients d1 and d2 are inferred directly from data by using this formula here. And in particular, d1 represents a deterministic damping, accounting for the structure breaking across the dynamical scales, and the red term is accounting for resolved plasma dynamics at mesoscopic scale. I mean, this modeling is performed. This model interpret these fluctuations, these fast fluctuations, as a stochastic source. Which drives the system continuously out of equilibrium, and we know that the solar wind is a system out of equilibrium. Okay. Okay. Okay, as I said, in this analysis we used Parker solar probe data, high frequency Parker solar probe data. The Parker solar probe was located at 0.17 astronomical units in this data period. We rotated the magnetic field in the maximum minimum variance reference system, and we perform a univariate analysis by considering only the maximum variance component. The results associated with the other components are not shown here. And most importantly, for this particular dataset, the Taylor hypothesis is valid as demonstrated by these other studies. Okay, in this presentation, the trajectories are reconstructed directly from data, And to do this, we define essentially a time window of the signal here, for example, of fixed width. And inside this time window, we compute the increments by fixing the starting point. And then we take, essentially, we fix this starting point, we take the difference with each point contained into this window. Here, for example, to this shaded region in blue corresponds to this fluctuation trajectory here. Then finally, by reiterating the procedure for each time window of the signal, we get this ensemble. And at this stage, we can see a difference of the trajectory's behavior in the inertial range and at sub-ion scales. I mean, for example, here we have more stochastic behavior, more irregular behavior, but here we have, let me say, a domination of the damping term. Skip this. Skip. Sorry. Okay. Before proceeding with the analysis of the entropy production, let me add that we performed a cross-check to make sure that the statistics of the fluctuations is correctly reproduced by our model, scale by scale. And to do this, we refer to the Fokker-Planck equation, which is basically the representation of Langevin processes at the ensemble level. I mean, in the space of probability. So we solve it numerically, and we compare the statistics it generates with the observations. We use these empirical coefficients, and this is an example of the estimation of these coefficients. We have that d1 is a linear function, d2 is a quadratic function, and the parameters delta, alpha, beta, and gamma are scale-dependent parameters, which behave as a power law, not shown here. Okay, then we insert these semi-empirical coefficients into the Fokker-Planck equation, and we solve it. And here, in the dashed black line, represents the solution of the Fokker-Planck equation. The colored lines represent the observation, the statistics of the increments, essentially. And as you can see, sorry? From large to small scales, yeah. Okay, and we can see that they are overlapped, and so we can conclude that the Fokker-Planck equation generates the statistics of observations. Okay, so we have that the ensemble of the individual trajectories in this framework is generated by the Langevin equation at the level of single realization, I mean. We have associated to each scale an ensemble distribution given essentially by the statistics of the increments at fixed scale. But since this probability distribution varies across the scales, we have to associate also the evolution equation of this ensemble distribution, which is given by the Fokker-Planck equation. Here, the scale in units of di, the ion inertial length. The fluctuation of the magnetic field. The maximum variance component. Yeah. Okay, as I mentioned, the interesting point of this approach is that we can associate to each realization of the process an entropy production. I mean, this formula gives us the entropy produced during the realization of each process, of the process, sorry. And this equation can be derived by simply from the Fokker-Planck equation, essentially, by computing the equation of motion of the entropy production by assuming the validity of Fokker-Planck equation, essentially. We have here two terms. The first term represents the irreversible contribution to the entropy production because it depends on the total trajectory. Here we have the red term represents the reversible contribution because depends only on the the start point and the end point of the trajectory. Okay, so we have this formula. We can compute this entropy production for each trajectory in the ensemble, and we get these distributions for each term in this equation. In particular, the black line represents the distribution of the total entropy production, and as you can see, this distribution is very skewed towards positive values. Negative values are allowed, and the mean value is positive. And let me say this is the fingerprint of non-equilibrium. Okay, more precisely, in the theory of out of equilibrium statistical mechanics, the entropy production is associated with the asymmetry under the reversal of the dynamics. I mean, this link in this statistical mechanics theory is expressed by the so-called fluctuation theorem. And according to this theorem, we can say that the mean value of the entropy production gives us information about the preferential direction of the process. In this case, in this framework, the integral fluctuation theorem in particular says also that the realization of in which the entropy production is negative, a realization in which the propagation is in the reverse direction. In this case, we verified the integral fluctuation theorem. Here we can see that the empirical exponential average converges to the expected value of 1. And in this case, since we are modeling the dynamics in scale and not in time, we can say that in our case, entropy consuming trajectories are associated to a behavior in which we have a growing of fluctuations from large to small scales. And to visualize this, here is a 3D plot in which I show the mean behavior of the trajectories conditional on the value of the entropy production. And here we have the value of entropy production. Here we have the dynamical scale, and here the mean value of the amplitude of fluctuations. And as the entropy production decreases and becomes negative, here we can see the development of this coherent fluctuation at close to the ion inertial length. Also, here I have the cut with respect to the entropy production value. As you can see, we have a trend according to which we have an increase of fluctuations from large to small scale with this coherent peak at the ion inertial length. Sorry. Okay. Here is a plot of the probability distribution functions, again conditional on the increments on the value of the entropy production. Here the green line represents the entropy producing trajectories. The purple line represents the entropy consuming trajectories. At small scales, we see that they are essentially overlapped. But if I evolve these distributions, we see very different behaviors. And in particular, the purple line inside the transition region develops these very high tails, these many outliers, and which are essentially the fingerprint of this peak. Okay, this behavior is also confirmed if we compute the flatness, again conditional on the value of the entropy production. The purple line here is again associated with the entropy consuming trajectories, and as you can see from large to small scales, here the flatness develops this peak inside the transition region, essentially. But the global average is dominated by the entropy producing trajectories. So their statistical weight is very low. And here on the bottom panel, I have I plotted the second order structure function. Here again, the purple line associated with entropy consuming trajectories in the inertial range behaves as a power law, but in the transition region we have a minimum, and then let me call this a range action of energy responsible for this peak, again consistent with this picture. Okay, coming to the conclusions, at dynamical scales from the far MHD range down to subion scales, the increments of the solar wind magnetic field can be described by a dynamical model by using a Langevin-like approach. And in the spirit of stochastic thermodynamics, we found that the increments of the solar wind magnetic field satisfy an integral fluctuation theorem. And this fluctuation theorem says that the entropy consuming trajectories have essentially an opposite behavior with respect to the entropy producing trajectories. And let me say that this behavior can be associated to the formation of intermittent structures in the scales compatible with the transition region, the ion inertial length. Okay. Thank you.
So we have 5 minutes question time, because then we have the coffee break. So Bill.
So your analysis is only looking at magnetic field, is that right? So that leads me to suspect that your definition of entropy is like a Shannon entropy or something, or it's not a thermodynamic entropy.
It is an equation of motion for the Boltzmann-like entropy, yes. So it's assuming the validity of Fokker-Planck equation.
So is it something, I don't know if you wrote a definition down, but is it the PDF of the magnetic field times the log of the PDF?
Yeah.
Yeah, okay.
Yeah.
So I have more a comment. If you were to do this instead of delta B, but you do this for delta V as well, and then if you compare them, if they look similar, then you probably can argue this all the turbulence now is aphanic. But if they are not, then you may say maybe there's some structures coming in. I'm just thinking that if you do the same, if it's aphane, then you should have very good correlation between delta V and delta B. So you could do the same thing for delta V instead, just only to do delta B. The problem is the data, I see. So high resolution data for delta V, don't. That's right. Great. The other thing is you showed as you go from the land scale to inertial to sub ion scale, the delta B3 is small for the ion scale, and then it becomes large. There was a figure.
This one?
No. Go back. Yeah. Yes, this one. So can I sort of understand this as you go to this inertial scale? You actually have this more like random walk, and at this smaller scale, it's more like linear motion. Is this a way of understanding this?
You can see the next. Simone will talk about this.
Okay, answer will be offered.
Any other questions? Oh, there we go.
Can you? I like this work very much because it shows how coherence appear, how coherent structures appear, and that they, how to say, are related to intrinsic scales of the of the plasma physics. On the one hand, on the other hand, they are related to the consuming entropy, which is very, very nice as an idea. And the question, my little bit about how you up the Langevin equation, how you have chosen the terms in the Langevin equation, because that's the starting point, isn't it?
The Langevin equation here is semi-empirical. I mean, the coefficients, d1 and d2, are inferred from data, essentially, scale by scale. So this procedure of fitting the coefficients is reiterated for each scale we considered in the analysis. So we, in this way, we have an estimation of the parameters of these Kramer. They are called Kramers-Moyal coefficients, and by fitting we have an estimate of delta, alpha, beta, and gamma, scale by scale. And as you can see here, the behavior of D1 and D2 are respectively linear and quadratic, and so we can fit these coefficients with a quadratic function and a linear function. And it is valid for all scales we consider it.
Okay, I guess it's time for a coffee break. We will have another coffee break instead of 40 minutes, because we are a little bit behind schedule, okay?
Was der andere da ist. Was der andere da? Da hinten vielleicht. Just trying to figure out which port.
None of them.
None of them?
None of them?
I don't know. I thought maybe.
No. This one is... No.
On the back?
Ah, you have to start, yes. It's this one. This one.
This one. Ah, okay. Let's try. Oh, it's already there. Now let me see presentation. Oh dear. Perfect. Thank you.
Enjoy the coffee.
Real thanks.
Prova a parlare.
Ma c'è un modo per bloccarlo? No. Ah, ok.
Vai.
Ok, ok. Aspetta, Vediamo dove sta il proiettore. Ok.
Okay, everybody. So welcome back. We will have the last two talk of this session, and then we will begin the astrophysical session, and we will also change the chair. So now we'll have a talk by Simone Benella, and the topic is Markov processes and stochastic thermodynamics as a new perspective for small-scale plasma turbulence. 15 minutes plus
Okay.
5 of questions.
Good morning, everyone. I'm Simone Benella from the Institute for Space Astrophysics and Planetology, and I will remind some concept in my presentation that Mirko Stumpo explained already before me. So essentially, my presentation is divided into two parts. The first part, I will essentially explain and make a link between the theory of Markov processes, so the representation of the statistical behavior of the fluctuations of the magnetic field as a function of the time scale, and the scaling properties of the structure functions. And in the second part, I will just extend the analysis in terms of production or consumption of entropy to numerical simulations of plasma turbulence. So this, Mirko already showed this picture right here. So we found that it is possible to calculate directly from magnetic field data first and second order Kramers-Moyal coefficients, that it is possible to solve a Fokker-Planck equation at least numerically, and it is possible to essentially reproduce the statistics of the process observed from data. So this is essentially a sketch of we mean by this stochastic process. So we have a fluctuation at the large scale associated with a given structure, and then by moving the process towards scale, by evolving the process towards scales instead of time, we have essentially fluctuation associated with smaller and smaller structures. So what we can say about structure functions? If we define the structure function like this, we can essentially take the Fokker-Planck equation, and we can multiply the Fokker-Planck equation by this b to the power of q, and we can integrate like this. So we obtain essentially a Fokker-Planck evolution in time scale for the structure functions of the process. So this depends on the drift coefficient and of the diffusion coefficient in terms of Langevin equation. So as I showed in my first slide, we essentially found that it is possible to accurately describe D1 and D2 by those simple formula, simple parameterization. This is essentially linear in the amplitude of the magnetic field fluctuation, and this is a quadratic term. So if we substitute this simple parameterization of D1 and D2, and if we multiply the derivative with respect to tau of the structure function by tau over structure function, we obtain essentially a logarithmic derivative right here with respect to the logarithm of tau. That is the definition of the local scaling exponent. So this local scaling exponent is has this form, this explicit form in terms of the parameters of the Kramers-Moyal coefficients. Just a naive estimation of the importance. If we of the importance towards different scales of the two competing terms, let's say D1 and D2. If you remind the picture that Mirko shows you about trajectories, so the more stochastic trajectories within the inertial range and the more damped trajectories within the subion range, We can, by comparing essentially the behavior of D1 and D2 across the scale, we can find that the ratio of the two terms of the Langevin equation is growing in favor of the D1 term. That is essentially the drift term. So I can say that the drift term is dominant, going towards smaller scales. So we make a super simple assumption based on this fact. So we assume that diffusion is negligible at these scales. This means that alpha and beta are approximately 0. And the equation for the local scaling exponent simply reduces to this tau dot multiplied by q times gamma of tau. That is the parameter of the first order Kramers-Moyal coefficient. So at subion scale, we assume this trend. We can see that it is empirically valid. These are, for instance, 2 feet of this relation right here at subion scale by using a Parker Solar Probe interval and a cluster data interval that have been analyzed in recent papers. And we find almost the same result for both spacecraft. So 0.8 times tau to the minus 1. Gamma is essentially a parameter which depends on scale, on the time scale tau, and defines essentially the drift term of the Fokker-Planck equation. Yeah. So in this framework, when you write down the Langevin equation, you have a deterministic part that is called somehow drift sometimes, and is the first order Kramers-Moyal coefficient in general. But people usually refer to this as drift because it is essentially sometimes related to a potential, so it is a deterministic part of a typical stochastic equation. Because you have also the second term that is diffusion when you have. Sorry? It's general. Yep. No, everything is in scale as a function of the scale. This yeah, this picture is. Look at this picture right here. So our time series that is a time scale process is going down. You have a fluctuation here at the larger scale. You have fluctuation here at a smaller scale, smaller scale, smaller scale, and you look at these kind of trajectories. Yep. Yes. Yep. So. Okay. So last thing that I said is that we found empirically this relation right here. So gamma scales in both cases as 1 over tau. So this relation is quite simple and is quite clear to us, because if you have one scaling like this and you multiply it 1 over tau by tau, you have essentially canceled out the dependence on the scale of this local scaling exponent. So you find essentially a global scaling exponent. But this global scaling exponent, QA, if you plot this, that is represented by these two straight lines right here, and you essentially evaluate from the empirical point of view the scaling exponents that are these dots that I reported here, you can see that they are fairly in agreement at sub-Boolean scale. So this is kind of way to recover this, let's say, global scaling invariance that we are observing from data at kinetic scales. So, yep, of course, that's my point.
But you just saw the structure. We just saw the structure.
Yeah.
How do you explain the existence of structures and non-intermittence in your results?
It, yep. It's clear. Yep. Local self-similar. Oh, it's interesting. Okay, let me move at the level of single trajectories. So, I mean, trajectories are essentially the amplitude of the fluctuation as a function of the scale. You can see the scale right here. These are Parker solar probe data in green, Langevin model that we fit from data with this magenta line, and let's say K41. I wrote K41 because when you assume that the diffusion of the scale, the processing scale is negligible, you are making an assumption that is similar to the K41 Kolmogorov theory, because the correctly way to have the Kolmogorov scaling from Langevin equation is essentially to only include drift terms, only deterministic trend in the equation. So you can see that for some kind of, there are some kind of trajectories where all these three, let's say, timescale series are fairly in agreement. So the global trend is captured also by the deterministic model that is essentially a damping through the scale. But and otherwise, there are trajectories that start to, due to the diffusion process, to diffuse in scale and to go out from the deterministic trend expected from this K41-like model. So, and we can see that essentially we have this kind of behavior in general. So is, let's say, a tendency going toward smaller scale. And when we approach the, this is the one di length, in scale length, when we approach this scale length, we can see that the diffusion starts to be important. So the process is, the stochasticity of the process is growing up. Yep. Of course, yes. This is the same model, but with also D2 term, so with the diffusion term. Yep. It sometimes happens. I just integrate the model, but I put this picture because also here you have kind of, this is more smooth going away from the deterministic trajectory, we have right here, for instance, a sudden increase of the fluctuation in scale. And we have this kind of behavior also from the Langevin model from a qualitative point of view. This is stochastic integration. So. Okay, let me move to the second part of this presentation, where I will essentially remind to the delta S, so production, consumption of entropy along the trajectories that Mirko explained in the previous talk. And in order to infer some connection with the physics at subayon scale, we investigate the entropy production by means of numerical simulations. So I will essentially show you result for a hybrid Vlasov-Maxwell model and the whole MHD simulation in the following slide. So what we do right here, we essentially consider this component that is an X component, so is perpendicular to the mean field that is an out of plane mean field. And essentially we cut with a certain angle this box several times by using the periodicity conditions, and we built a time series from this, let's say the equivalent of time series. So this is how, for instance, a snapshot of a scale series from the whole MHD simulation look like, and this is the Vlasov-Maxwell one, and they are compared with piece of Parker-Solar probe observations. And if we build the trajectories, the ensemble of trajectories, so the fluctuations of the magnetic field as a function of the scale, you can see that from a qualitative point of view, in both these simulations, we have this stochasticity that is dampened in some sense at subayon scales. So this is quite well reproduced, at least from a qualitative point of view. And if we look at the statistics also of the delta S, we can see that it is fairly in agreement with previous results shown by Mirko Stumpo and calculated on the Parker-Solar probe data. So we have this skewed distribution that are essentially a clear signature of an out of equilibrium system. And in particular, we can see that the average entropy production is, of course, positive. Also, this statistics is quite well reproduced in both cases. And let me move to the to visualize how the values of the entropy production or consumption are essentially located when we draw the trajectories and we color the scatter plot with the associated value of delta S. So I report here the values of the absolute values of the currents in order to look at the structures. And we can see that, in general, there is a complicated, let's say, relation, not straightforward, because between this quantity and this one. But we can see that, let's say, most probable values that are the core of the delta S distribution between 0 and 10, 12 are sometimes located in this region that corresponds to coherent structure seen here in the density current plot. So also here you can see that there is a quite nice correspondence. This is the result that we obtained on the whole MHD equation and whole MHD simulation. And again, we can see that these hotspots are fairly in agreement with the structures that are observed in the current pattern. So in order to infer some statistical relation between these two quantities, so the absolute value of the current and the production consumption of entropy, we just studied as a, this is a kind of preliminary result, let's say, and we studied the association by evaluating the conditional probability of the values of the current conditioned on the delta S. And we can see that essentially for values of delta S that are lesser than 0, we have an increasing trend in both simulations. We have an increasing trend of the mean value of the current. So This is, at this stage, quite preliminary, and we are trying to interpret this result that is not straightforward at this point. And I like to highlight that the complex knowledge of a current structure allows us to investigate this association between the stochastic entropy and the magnetic structure of the current sheets. And this is, in general, related to lower the production of entropy is generally related to lower current values. So this means that essentially we are kind of locating our delta S, negative delta S values on the borders between the magnetic structure. So where is located the higher values of the current, so current sheets. So I must say that the stochastic entropy does not provide a truly local information, since delta S is essentially a quantity that is integrated over the whole trajectory. So it is not a truly local information. And so that's it for me. I thank you for your attention.
Very nice, thank you. We have a question from
the slides where you show the delta S on the wall box, please.
This one?
Yeah. So if I understood it correctly, delta S is integral in space, so you're in scales. So you're considering all the scales from the smallest you can resolve up to the largest one, right?
Not exactly. We fix a window that is 10 di, right? 10 di.
10 di, 10 di around centered on one specific scale, or?
So the association between the data point and the color here on this scatter plot is made by considering a point in time, fix the time, and then build the set of trajectories that we need to perform the integration. And that we associated this integrated information to that point, just to have a look of the distribution in space of the values of entropy. But this is the reason why I point out that I like to stress the fact that this entropy production is an integrated quantity. It's not truly local. But for the Markov condition, you can chop the time series whenever you want. So we decided to take 10 di.
Okay, but what I was thinking is that if you want to do a better connection with this entropy production and the structures, for example, in current, would it be possible, for example, to integrate delta S over only a limited portion of the scales you're considering? Like, for example, up to the smallest scale, you can resolve to 1 di, and maybe in that case, delta S would be higher correspondent to the structures. Because you're also only considering the structures, the scales of the structure you want to look at. So maybe, I don't know if it makes sense.
Yeah, that's a good point, actually.
My question actually is related to this one. If I look at each point over there, where you calculate this entropy delta S, it's actually include, the trajectory will include points nearby. So each point over there is not that single point.
Yep.
So the suggestion over there is if you do integrate a sum over other points around your structure, then you can get more or less sort of the average delta S for that structure. Okay. Yep. And your resolution of 10 di would be each point over there represent the trajectory will cover a 10 di sort of spatial, roughly a spatial.
Yeah, of course,
region.
That's true. But here we are not considering windows of 10 di's. We are considering actually a windows of 10 di's to calculate the trajectories, but then we move of one point and do the same thing.
It can really go to other part of this this diagram. Okay.
Yeah.
Okay, thank you again to the speaker, and we move to the last talk of the session. You can. Yes, you can while Giuseppe is setting up.
Maybe if it's the mirror story, you can try not implement but something else. Because implements are looking for planar structures. And we do not observe planar structures in survival, but more vertical structures. So maybe you just need to take another definition of your fluctuations at different scales and try to see what you get.
Yeah, good suggestion. Thank you.
The last way. Ma non lo so, boh. Vedrò, uno dei due. Dammi il puntatore. Okay. Okay, thank you. So let me see if I've organized complex stuff. Now, my talk is a little bit different because I would like just to pose some questions about what happens when we move from the inertial range and the non-MHD scale. So this is a work that is done in collaboration with Tommaso, Emanuele, Oreste, and I have to thank also Simone and Mirko for the insights they provide me with their presentation and their studies. Now, the point is the following. We have now a large evidence that when we move to the small scale, so the non-subion scale or something like this one, essentially we have a pattern, a specific pattern for dissipation. Now, generally, we treat this problem in terms of just of a discussion of specific mechanism to generate this pattern. I would like to pose a different question. Why nature needs to generate a fractal pattern for dissipation? Is this just incidentally, or is it due to an optimization for the dissipation process? So this is something that it's a really important question because when you deal with nature, sometimes nature create fractal structure because this fractal structure optimize some specific function. And so I would like to discuss essentially on something that is related to what we call in a different context as functional order. So you generate something that is the results of coherence between fluctuations that generates a fractal pattern. So the form, the shape is optimized to the function. Now, we know, I don't know to repeat these things, that one very critical issue is that if we move from the inertial range to the subion scales, we observe this strange behavior. This is a recent paper by Chilber. You can see that you can observe anomalous scaling for the exponents in the inertial domain, in the let me say transition region. Here we see a transition region. Sometimes we don't see this depending on the region we are looking to in the heliosphere. But if we go to the smaller scale, we got essentially a straight line. So this is something that seems to be a controversy. Okay. Now the question is the following. Oh, you have already seen this. Is a Parker solar probe. Yeah. It's the same period that they have already shown in the previous presentation. Sorry? Is SCAM. Yeah, I think that these are SCAM data. Now, okay, I can see here. The observed scaling invariance is accompanied generally by spectral features, and these spectral scaling exponents are contained in this interval, 7/3, 3. You can also enlarge this window. It depends on the specific point. You have to take into account that when we deal with this turbulence, we have to have ensemble averages. Otherwise, we cannot deal with the specific period because the spectrum fluctuates extremely in time. Extremely point by point. This is very clear if you perform shell model simulations. You can see that the spectrum moves continuously, but if you average in time, so if you assume ergodic properties, you can get the right spectrum that is expected from the theory. Now, in the 1996, Sasha Milovanov, and also you can see the paper by Zilioni and Milovanov 2004, they essentially proposed a scenario to link the percolative pattern of the current topology with the spectral features. And they say that essentially the spectral feature, the spectral exponent, is related to the dimension of the percolative pattern of the currents. They imagine essentially something that is this. You have, if you want, you have coherent structure. You can call coherent structure. And then you have just a current that moves around this coherent structure. Bundles of fluctuations, if we want to use a terminology that was introduced some times ago by Tom Chang in a different context. Now, there is this relationship from the dimensionality of this pattern, percolative pattern, and the dimension of the spectrum clearly in the kinetic subion. I don't know how to call this, non-MHD scale, non-inertial range. So let me say something like this one. There is also another very important concept that was introduced in the theory of percolation, and there is this which is called the Alexander-Orbach conjecture that essentially allows to compute some. This one, no. This is related to, because I just put this number. So generally observation finds something between 7/3, 8/3, minus 3. If you have a steeper, you can clearly, yeah. There is a limited value because I think that this is when ds is exactly the embedding dimension of the space, which is 3. So in that case, you recover something that is -5. So this is something that I would like to underline. Now, there is this, which is a connectivity index, which represents essentially a measure of the obstacles, the relevance of the obstacles in the flowing the currents. Now, these are some simulations that I got from my friends. So you have already seen this. This is from Emanuele Papini, and this is from Oreste. So these are two different, essentially, simulations. And okay, I try to extract the current topology. Now, instead of studying the statistics, I have used let me say, a method. I compute the mean value plus 3 sigma. Then I remove values larger than 3 sigma, and then I compute the mean value. So this is a self-consistent way to estimate the threshold, which is this one. And if I cut this image and I binarize this image into two black and white, 0, 1, I got a pattern that is much more significant because it's related not to the fluctuation, the noise that you have in the signal. Now I can compute the dimension of this, and I can apply, for instance, the standard box counting method, and I got to find the self-consistent threshold, because if the distribution function contains essentially two contributions, you have to separate these two contributions. How do you separate this? So this is the way how they apply. They apply the similar method in analysis of solar phase and shell model relaxation events in the Boffetta Carbone many years ago in the PRL paper. So this is a self-consistent threshold. Once I've done this, I got something, and this is the average dimension, 1.82. Now, if this is the dimension of the pattern, okay, so the fractal dimension, using the approach by Sasha Milovanov and Zilioni, I can compute the exponent, which is 2.64 plus or minus 0.54. I can compute the Arcetri exponent, which is very similar. And I can compute to what has been already shown by Simone, and I can compute the connectivity index. This means that the current pattern is not space filling. So this is something that is a fractal structure. Now you can say, okay, but current, the intensity change point by point. So I can do the same analysis by applying the multifractal analysis, and I can recover the D2 Rayleigh dimension. D2 is the dimensionality of the pattern, because it's the correlation dimension. While D0 is the dimensionality of the system where you put the measure, and this is 2 because I have an image. So this is the support, the dimension of the support. So this number is consistent with the previous one. And if I should be, because in the definition of fractals, and this D0 is the support, and the support is an image. In this case, I am defining a measure over 2D images. So the support is 2. D1 is named information dimension. D2 is the correlation dimension, which is the real dimension of the fractal pattern. Okay. Sorry? The Hausdorff, exactly the Hausdorff. In fact, I forget to say I have written here that D2 is equal to the Hausdorff dimension, DH, which is the dimensionality of the pattern. Now, this is a comparison with the range of variability between the spectrum that I have just computed over the image using Bx and By, the two components, and the estimated range of variability for the power law from the topological analysis that I have done. Yeah. That's right. Is a 2D. If the real 2D, if a 3D, you can get clearly -5. Yeah, because I'm analyzing, because the support I've defined on an image. Yes, but if you provide me a box, a 3D box, I can define the support in 3D. But electron scales, okay. But it means that essentially, but you have a box or you have just one a plane, a 2D. Okay, this is something that, yeah, probably. But you have a 2.5 because you have something that also can get some information on the Z component essentially. Okay. No, because this simulation 2D. But in any case, in the solar wind, it is supposed that the turbulence is mainly 2D. There is a strong anisotropy. So, yeah, yeah. Now, okay, I can compare with the structural function, and the 0.82 is quite good when we go to the subion scales. And these are the results for the Vlasov-Maxwell simulation, which are exactly the same. So we got similar results. So there are no difference between the exponent that we found. They are inside the errors. So we can say that there are no substantial difference at this scale. This is a good news because this means that things are essentially converge at the same, describing the same kind of physics in some sense. Now, let me move to the point. What is the origin of this fractal pattern? So this is the question that I want to pose to the audience. Something like a take-home message, something that we can do in the future, okay? Now, we have the generalized Ohm law. Everybody knows very well this. Then the entropy production rate according to the Groote-Mazur, but you can find everywhere. It's just we can apply the first phenomenological law, so we can just multiply in fluxes for thermodynamic fluxes for thermodynamic forces, and we got something that is expressed in this way. Now we have done the assumption that the pressure tensor is essentially homogeneous. So I have neglected the non-diagonal terms. So this is just the pressure, okay? And so we have different terms here that can produce entropy. So these are the product by T and sigma. This is exactly the quantity of heat that you provide to the system. Now, these two terms, okay, now the question is, J square and these are connected each other? The answer is yes. Yesterday also, Luca showed some of these pictures. So I have attempted just a very brief analysis, but there is a good correspondence between the two. So I would like now to concentrate on this for my discussion, to J square. And I have done the same analysis that I've shown before, so finding a different dimensionality clearly, because when you square the value, you are looking to enhancing the region, and so the threshold cutting the structure change. And this is less, this means that dissipation is less space filling than J, okay, itself. Now I can do the same for the other quantity, and numbers are always the same, so that the question is the following. Is this due to the emergence of coherency in out of equilibrium system? There is a reason why we have to generate a fractal pattern for energy dissipation. Is this the best way to optimize dissipation in turbulence, okay, in plasma turbulence? This is something that, for me, it's extremely relevant. Now, in biochemistry, there is a very famous concept, which was introduced in terms of functional order to explain the emergence of correlations between fluctuations that occurs in time in that case. But we can rephrase these things, and so we can, okay, thank you. So we can say that is the fractal pattern related to something that a phenomenon similar to the functional order, and I can say that in a sense this means that we should have coherent structure, and coherent structure are formed by the spatial and temporal correlation in the fluctuations. So these are not in disagreement with your picture. The way is different because the concept I want to study is this. Is a fractal pattern the optimal topology to dissipate energy? And so, in completely different topics, river and also thermodynamics of fractal networks, they found that optical channel networks are fractal structure, optimal. So this is something that is important, and also that there is a criterium that essentially associated. Okay. There is a criterion that associates a minimum energy principle to the fractal structure of drainage networks. So there should be a more profound reason why turbulence generate these things. And I'm just trying to put, this is my last slide, apart from something very... Is not that, no, the system, what happens in turbulence? You feed the system with energy at a large scale. Then you have the stochastic cascading process that generates a structure at the end. And this structure should is the dissipative structure. This is the standard view also in fluid turbulence. Now the question is, this structure is the most efficient way how to dissipate the energy I'm feeding inside, and the topological features of this structure depends or not from the energy transfer rate, for instance, depends or not on which parameters. So in that paper, they found that applying a minimum energy principle, they got the optimal fractal pattern for river drainage. So this is the difference. So the question is this one, and a way that I can just trace is this one, is the following. I can write the entropy production rate. Okay, now the entropy production rate in this case is expected to be on a fractal support, phi di, d here. Now I can just compute this using a fractional calculus introduced by Tarasov et al. So this is the embedding dimension, which is larger than phi, okay? Because it's the embedding space containing the fractal structure using just a renormalization factor. And then I can say, okay, I can try to optimize this quantity with the constraint. And if I can be able, I'm not sure to be able, but if I can be able to do this evaluation, I can get some information on the dimensionality of the fractal pattern as a function of the epsilon, which is the energy transfer rate along the turbulence cascade. In this sense, why we have monofractal behavior at that scale? Because you have generate, essentially, the topological structure, and this is that optimize the energy dissipation, and you have generate a fixed point. And so you are a fixed point for statistics that is non-Gaussian because you have a fractal structure and it is all at the same time monofractal. So this is, I hope to have some progress next year. And just to remind you that we have 200 years from the born of, from the death of Antonio Canova. You can visit this place in Florence. Okay, thank you.
Questions?
No, I'm very interested, you know, but it's just a problem of understanding. If you take the classical power law, which is predicted in terms of Gaussian PDF, etc., in the kinetic range, you should have 7/3. Yeah, equal argument. And in that case, the Philip factor should be 3, because you should fulfill completely
in 3 dimensions. Yeah.
But from your formula, it doesn't happen.
No, it is. So you generate something that it is 7/3, okay? But the pattern you have of the current.
Using the Kolmogorov argument.
Yes, but you can generate. You have to generate some patterns there, some structures. I'm not talking about the fact that in this discussion that the distribution is not Gaussian. There is no link. I'm just looking to the current patterns, okay? And the current patterns is something that has that slope.
It's just,
Not a Bayesian scale.
No, the argument beyond the fact that at the high scale you should have 7/3 is the same argument of Kolmogorov.
But also no.
Yes, but just I'm just okay.
Slightly increases by the very low.
Just because in the argument you assume that you can okay, basically you could have a monofractal behavior.
You can have a monofractal mirror. The idea I have in mind is the following. You have the injection scale. No, yeah, but you have the injection scale. The injection scale generates the cascade. The cascade generates the fractal pattern. This is multifractal. Yeah, but you are, at that scales. It was done for all. Yeah. In the EMHD turbulence. But you generate structure even in that case. You generate structure. Exactly.
Sorry, no. We have just one last question from the top of the audience who's behaving very well, and then we switch to the next session.
So a couple of comments actually. First of all, I don't know why Careri was speaking about functional. One has not to misunderstand this. We are not, because nature seems to have an intention, so to speak. The leaf has that structure to better survive, etc., etc. We shouldn't speak about functional in the sense of an intention. Sorry for the philosophical digression. But no, because actually it is something like maximum or minimum stationary action principle. So nature does not have this is how it works. So trajectories taking place in a classical physics do minimize or extremize S, the mechanical action. Okay. So this is the same kind of ideology. As far as your quantity that you would like to extremize is concerned, I have made a couple of calculations this morning just after breakfast, and I send you the snapshot of the blackboard at home. Actually, I am afraid that this dimension has to be related to the local properties of J, for instance, and P. Otherwise, you simply find something which is clearly reasonable. In order to maximize that quantity, the dimension has to be 3, simply. Because, of course, you smear all over the support space, okay? So D must be a function itself of the local fields, which is very reasonable in microscopical terms.
If it is a multifractal structure, yeah.
Yes, and this is
for dissipation.
So it will be beautiful to make these calculations.
Yeah.
Okay, let's thank all the speakers of the session. While I am handing in the power to the next chair, so I just want to say something. We found yesterday this pocket here that was left in the room. I don't know who belongs to. So there are like pens inside, style. So whoever knows who is the owner of this, please let me know.
Okay, so it's time to move to the fascinating session about astrophysics beyond the heliosphere. Our first speaker is Federico Sabatini, who will talk about machine learning model applications to galactic cosmic rays. So whenever you're ready, you can start. You have 15 minutes plus 5 of questions, but it's a little flexible. Please.
Hi, everybody. I am Federico Sabatini, and I am a computer engineer and a PhD student at the University of Urbino, and I'm going to present some machine learning models that I developed that are based on the galactic cosmic ray observations gathered on board the European Space Agency LISA Pathfinder mission LISA Pathfinder. So I'm going to provide a brief introduction about the involved space missions. Then I will present my machine learning models, and finally I conclude with some possible future investigations. So during my past thesis works, I studied the effect of the interplanetary magnetic field of the interplanetary medium from the point of view of high energy particles for the LISA mission and the future space interferometers. And I learned several important lessons with the LISA Pathfinder mission. That was the precursor mission for the LISA mission. So I briefly recall that LISA Pathfinder was launched at the end of 2015 from the Kourou base with mission end on July 2017. It orbited around the first Lagrangian point at 1.5 million kilometers from Earth, and it hosted a particle detector that was able to measure the integral flux of the galactic cosmic rays and of the solar particles having energies above 70 MeV per nucleon. So thanks to the particle detector on board LISA Pathfinder, it was possible to study both short-term and long-term variations of the galactic cosmic ray flux. And these particle detectors is composed of two silicon wafers of 1.4 times 1.05 square centimeter of area, 300 microns thickness. And the wafers are disposed in a telescopic arrangement at 2 centimeter distance inside a shielding copper box of 6.4 millimeter thickness. So this is the future LISA mission that will be the first interferometer dedicated to the detection of gravitational waves in space between the frequency range between 2 times 10 to the minus 5 and 10 to the minus 1 hertz. There will be 3 spacecraft in a triangular formation, and this spacecraft will host magnetometers to detect the passage of large-scale structures. So it would be very interesting to study both galactic cosmic ray short-term variations and solar energetic particle events. And currently, the European Space Agency is designing a particle detector that will be able to observe both events. When we have to study the performance of an instrument that will be placed on board a space mission, we need to carry out predictions before the mission launch. And for example, for LISA Pathfinder, the flux of galactic cosmic rays have been estimated for protons and helium for the first phase of the mission with the Gleason and Duxford model. And in the figure are reported the estimated lower and upper bounds. And in the figure you can also see the middle lines that are the AMS02 data that appear in agreement with the estimated lower and upper bounds. The galactic cosmic ray flux observed in your heliosphere is composed almost entirely by protons of galactic origin, and it is subject to long and short-term variations. Long-term variations are associated with the solar activity and polarity with periodicities of 11 and 22 years respectively. Here you can see, on the other hand, the short-term variations. So in this figure are reported the galactic cosmic ray data gathered on board the LISA Pathfinder mission during the whole mission lifetime. You can see that the trend is increasing because the mission orbited during a period of decreasing solar activity. And you can see more than 40 galactic cosmic ray short-term variations that may be recurrent, as this one highlighted in blue, when they are associated with the passage of solar wind high-speed streams, or maybe non-recurrent, as these Forbush decrees highlighted in red, when they are associated with the passage of the interplanetary counterpart of a coronal mass ejection. I recall here that in this plot, but also in the following, you will see 4 panels. In the first one, there is the LISA Pathfinder galactic cosmic ray observation. In the second one, the solar wind speed data gathered with the ACE experiment. And in the last 2, there is the X component and the intensity of the interplanetary magnetic field gathered by the ACE experiment. And I recall here that the machine learning models that I'm going to present are optimized for galactic cosmic ray short-term recurrent variations, only for recurrent variations. So they are not supposed to provide good predictions when we have 4 Bush decreases. Barter rotation, yes. Okay, what? The intensity of the interplanetary magnetic field. This one? At the passage of the interplanetary counterpart of a coronal mass ejection. So now I'm going to present this machine learning model that I designed. The first one is a neural network having 3 layers, so only one hidden layer with 375 neurons. And this neural network is able to reproduce to predict the LISA Pathfinder galactic cosmic ray missing data that were missing due to hardware testing on board the satellite. And the predictions are reported in red in the top panel. And you can see that the model is able to obtain good agreement with the data gathered right before and after these missing periods. So I used as input feature 18 input features. One is the galactic cosmic ray flux value 9 days before the instant to be predicted. And then I take 9 days of preceding observations of the solar wind speed data and of the interplanetary magnetic field intensity. And in particular, one observation is every 36 hours for the solar wind and one observation every 24 hours for the magnetic field. And so I have 18 input features, and I use all the available data set that are about 11,000 of instances. I use 10% as a test set, 8.5% as validation set, and all the rest as a training set. So after having trained this model, I use it to fill the LISA Pathfinder observation time series. And in this way, I have 18 complete barter rotations, and I can train another machine learning model, this time an ensemble model composed of 10 different support vector machines. And in this case, I want to predict the LISA Pathfinder galactic cosmic ray observations, not for small periods of a couple of days, but for a whole Bartel's rotation. And the results are reported in the top panel as green dots. The red ones are the predictions of the other model. I use the same 18 input features as before, but this time I change the dataset splitting because I have 18 Bartel's rotations. I use 3 of them as a validation and test set, 2 for validation and 1 for test set, and the other 15 as a training set. So the model is able to achieve an acceptable agreement with the LISA Pathfinder data. Then, since all these models, both the neural network but also the ensemble model, are machine learning black boxes, so they do not provide human interpretable predictions, I tried to apply symbolic knowledge extraction techniques, and in particular the GridX and CART algorithms, to the ensemble model. The model is the same that I just described, but I use the whole data set to train the data, so I overfit the training because I'm not interested in drawing predictions with this model, but I only want to extract human interpretable knowledge. So from this preliminary study, we are able to observe that the ensemble model is very similar to the expected data, and the interpretable models are are able to mimic the black box only if they are actually very poorly interpretable for humans. For example, if you look at the pink line, we have a decision tree with 500 leaves. So it is very accurate with respect to the black box predictions, but we have 500 leaves. So yes, it is a decision tree. It is human interpretable, but actually it is not. In this case, if you look at the green line, we have a decision tree with 10 leaves. So yes, it is very human interpretable because we only have 10 rules, but in this data period, it provides very, very poorly accurate predictions. So there is this trade-off between fidelity and readability that requires further investigations. Then this is the last model that I'm going to present. This is different from the others because the galactic cosmic rays observed with LISA Pathfinder are not the output of the model, but in this case, these are the inputs. And this model is trained to reproduce the solar wind speed data on the basis of the galactic cosmic ray recurrent variations. So why is important this model? Because, for example, on board LISA, we won't have any instrument to observe the solar wind speed. So we won't have nearby missions, as in the case of LISA Pathfinder, that may rely on the data of the nearby ACE or wind. So we won't have any clue about the solar wind speed data, but with this model we are able to, since on board LISA we will have a particle detector for galactic cosmic rays, we have a mean to derive some clues about the solar wind speed data. Of course, also this model is not supposed to work in an acceptable way when there are 4 Bush decreases, as in this case. So you can see here that the prediction error is higher. But it is not a problem because on board LISA we will have magnetometers, and we are able to reconstruct the velocity of the structures when we have 4 Bush decreases. So by merging the predictions of this model with the data gathered from the magnetometers, we are able to obtain the whole predictions. Thank you. So in this case, this is a 4-layered neural network. The data set have been splitting by using all the available Bartels rotations, 15 for the training set, 3 for the test set. And I do not took apart data for the validation because I use a 5-fold cross validation on the training set. And as for the inputs of this model, as a first step, I performed a 3-hour moving average to smooth the data, both the input and output data. And to predict a single solar wind speed data point, I use 49 input features, 49 past observations of the galactic cosmic ray flux, and in particular, 1 observation every 3 hours during the preceding 6 days. And so in the future, we want to enhance the machine learning models for the galactic cosmic ray short-term variations, because there may be other variables to be considered as inputs. But we also want to consider other machine learning approaches that at the moment so far are not have been considered. And analogously, we want to enhance also the machine learning model for the solar wind speed data, because this is a very preliminary model, and we want to perform a more accurate hyperparameter selection for the presented neural network. But also we want to consider different models as support vector machines or ensemble models. And since these models are, as the others, machine learning black boxes, we want to apply symbolic knowledge extraction techniques to these models. So for me, it's all. Thank you very much for your attention.
Okay, so thank you, Federico. Are there any questions from the audience? Yeah.
This
Wait.
So this X4 model, this is the force field model. If you look at this average time a GCR stay in the solar wind, it's sometimes depending. No, the X4 model, the original, the model shows this modulation.
No,
the very first, the Yen X4.
This is the first.
Yeah. This one. Now, if you look at different energies, basically they have different times staying in the solar wind. Normally they are over 20 days, and in some cases 30 days, depending on the energy. So in your machine learning technique, you only use up to 9 days. If you were to use longer period, that will be more accurate.
We perform several tests by both to select the dimension of the preceding time windows, but also to select the granularity in which taking the observation. So we found that there is not sensible difference between 9 days or 12 days, or between 24 hours or 12 hours, for example. There is some difference, but it's not dramatic. But these are the best parameters. So we also noticed that 9 days for the galactic cosmic rays is reasonable because it is the third harmonics of the sun rotation, and for the solar wind speed and the interplanetary magnetic field intensity, 9 days are the average durations of the galactic cosmic ray short-term variation. So they provide good results experimentally, and they have a significance from the physical point of view.
We have time for another couple of questions, if any. Otherwise, in the meantime, I can ask something.
Yes.
So, is it correct to say that with your machine learning algorithm, basically you are able to fill in the gap more like at larger scales, while you're probably missing the small scale structures, right?
Yeah.
Okay. And I was wondering, is this quite general? So, could you possibly apply it to missing data for other spacecraft missions, other measurements?
It depends, because in this case you need solar wind speed and interplanetary magnetic field intensity measurements taken nearby. So if you have these instruments on the same space mission, yes, you can do it. If you have nearby mission that take this kind of measurement, yes, you can. But if you have
do you need the actual 1D time series, or you can do it also like in some kind of statistical way? If you have like two spacecraft which measure different fields which are separated, then you can assume that statistically you're measuring the same parcel of plasma, for example.
I only tried in this way, so probably we can infer something with data manipulation, but I am not sure about the possibilities.
Any other question? Okay, so if not, let's thank Federico again. And we can move to the next speaker, which is Doris Follini, which will talk about 2D peak simulations of relativistic reconnection in ion-electron plasma. You have 15 minutes. I will ring the bell when you have 3 minutes left. Need help with this?
It's on the ear like this. Something.
Yes, perfect.
Stays.
Okay.
And
whenever you're ready.
Yep. Trying to fix that with the glasses. Hope this works now, and we do have a pointer. Yeah. Perfect. No, I go for the modern thing. Okay. Hello, everybody. I hope you can hear me. So this is joint work together with Rolf Walder sitting up there and Mark Diekmann from Linköping University. And I also want to mention two other people, Jean Favre from the Swiss Supercompute Center, who has been helping us since years with detailed visualization and data analysis issues in many projects, also in this one. And especially Michael Melzani, who actually got us started on this topic nearly a decade ago with his thesis work. And I put the paper he published down here, and you can say, well, it's, look at the dates, it's 2013, 14, why are you still working on that thing? And some among you may remember standing me here some years ago with exactly the same title, I did it on purpose, and presenting basically his results. Now, the simple answer why I'm again standing here with the same title is the parameter space is big. A bit more specifically, the specific corner of the parameter space we are interested in because of microquasars, I'll come to them in a second, is what you may call semi-relativistic, meaning we have electrons that are clearly relativistic and ions that are so-so, somewhat relativistic or not really. And that means, at least from a computational point of view, we're a bit challenged because we want to resolve the time scale the electrons move on, forcing us to a small time scale. But we're also interested in the ion physics. Also because you have observational data from these microquasars that suggest that ions play a role. So what Mikhail did in his thesis was using a reduced mass ratio of ion to electron mass of 25. And now you all know a proton is heavier than 25 times an electron. So the overarching goal of what I'm going to present here was to explore the parameter space in overall the same corner, but trying to fill qualitatively, quantitatively, and ideally with some physical insight, the gap between this reduced mass ratio and going to realistic mass ratios. And on the way there, also looking at magnetic fields, guide fields as influence parameter and reconnection rate. So just two words on microquasars. What are they? As this is more a solar physics community I take. So a microquasar basically is a stellar size, stellar mass black hole and a companion star mass from the companion star falling onto the black hole, producing lots of interesting physics, accretion disk jets and so on. The asset is we see them, they have human scale time scales. You can do a PhD on time-dependent data with them. They're also interesting as they are kind of related to larger scale relatives, active galactic nuclei. They do particle acceleration and so on. And we've got interested in these objects from an astro point of view long ago and look at them from different angles. You hear more about hydrodynamics, adaptive meshes going from 10 to the 14 to 10 to the 9 this afternoon by Rolf. In reconnection, they're interesting because by and large there should be magnetic fields for different reasons. In what I just described as a semi-relativistic regime, so electron magnetization 0.1 to 10 to the 5. And if you look at observed spectra from them and people just feeding in assumed particle distributions to reproduce kind of the colored symbols here of observed data from microquasars, they come up that they need hard non-thermal tails. So P to the 1.7, 1.8, something like that, which can maybe done with reconnection, but not with anything. So this I basically already said. I just want to highlight the somewhat recent paper by Werner et al., where they had a realistic mass ratio, but varied the magnetization and some other parameters, and they come up with, one of the conclusions is the regime we are interested in, this semi-relativistic thing, there the mass ratio really kicks in and changes results. Now what we look at, what's kind of our computational pet is such a Harris sheet, so you have kind of a magnetic field in one direction, the other, it's sketched here again, and then when reconnection starts, plasma flowing in, the exhausts here a sketch, that's the X point, the islands, you know that. So we set up a rather big box, computational box, something like 8,000 by 10,000 computational cells. We have something like 250 or more time step per electron plasma pulsation period. We have something like 10 grid cells per electron inertial length. And we let the thing evolve freely, so we get kind of multiple X points and plasmoids upon start. And we then analyze our data by separating our population into particles that have been really far from where reconnection will start to happen, and really far meaning 6 half widths of the current sheet, or if you want, you have background density, and on top of that you have the sheet we initialize, and the green population. We're analyzing the green stuff in all the remaining slides. That starts where the sheet population has dropped to less than 10 to the minus 6. So it's really particles we're analyzing that have been far from the reconnection side at the big, when we set it up. And we track something like 150,000 particle pairs, of which we have really all the data they see at high time resolution. Just to illustrate again the regime, so that's the regime we are. If you cut through an X point here, you have inflow from here, and then you see here the ion diffusion region starting, and here the electron, and it's really, we have a cold upstream flow, meaning 10 to the 8 or so we have really sharp boundaries of the diffusion regions. Parameter study, we vary the mass ratio from pairs to realistic, magnetization up here, I mean, it depends a bit what you take, so roughly from 10 to 1,000 for the electrons, and from 0.2 to maybe, or 0.1 to maybe 60 or so for the ions. We have a guide field that has a strength between, is not there, or up to twice the reconnecting field, and we've populated our space by some 40 simulations. Now, all the data I'm going to show you in the following, or most of it, is time averages or statistics on time. And that's now a timeline of one simulation, so that's kind of close to the start. Plasma will be flowing in from here and here. It's electron density, and then the plasmoids form, see here. And so, if you look at this as a time series, shown here is the change in the kinetic energy of the particles as compared to the change in the energy in the reconnecting component of the field. So something at the beginning is happening, but then something quasi-steady settles in when you're around here. And we analyze this here in mean and standard deviations. So most of the plot will be on this region here. Now, first thing we were interested in, what fraction of the reconnecting electric field energy that is, gets freed upon reconnection does end up in the kinetic energy of the particles. Any particles now that move. And most interesting for us was this mass dependence, and you see as the mass increases, the mass ratio of the ions to the electrons from pairs down here to a realistic mass ratio, we go up from something like 60, maybe 70 to 80% of the energy going to the particles, really. A guide field has the opposite effect, so you get really efficient transfer of energy, and it's only the reconnecting component of the field, not the total field. We get really a lot of field energy to the particles in the absence of a guide field, and then it really drops. Somewhat similar for different mass ratios. That's the role of magnetization. For sake of time, I'll not comment on that any further. Then you can ask, where does the remaining energy go? It goes to the X component, so the exhaust component of the magnetic field, and to the reconnecting electric field. And also dependencies there. Now we've transferred the field energy of the reconnecting field to the particles. Now we have been asking how much of this particle energy goes to the ions and what goes to the electrons. So what is shown here is the total, the energy going to the ions as a fraction of the total energy in the particles in percent. And again, down here, the dependence on the mass ratio. And you see the heavier our ions get, the more of the energy they get. So 80% for a realistic mass ratio, but only 60% for a reduced mass ratio, which Michael in his thesis used as he didn't have compute resources to do all the experiments over here. A guide field, interestingly, brings kind of the ions get without a guide field something like 60–80%, somewhere there, of the total energy in the particles. As we apply a guide field, we drop below 50%. Interesting here also is, I told you, we actually look at particles that are initially far from the current sheet, the background particles we call them, as compared to the current sheet particle, those really close to the center. If you look now here to the sensitivity for the guide field, you see that only these background particles that are far from the current sheet initially are sensitive to the presence of a guide field, but not those in the current sheet. And it doesn't matter too much where I decide.
Sorry, could you remind me what are the three numbers there? So one is the mass ratio, right? The one in the middle, in the legend,
the legends here, oh, that's just different colors. You can draw lines through points of different colors. They are identical except for the quantity down here. So the blue dots here have identical simulation parameters. The only parameter differing between these dots is the guide field. Apart from that's, for example, that's for a mass ratio of 800 and a magnetization in our units of 12 and so on. Exactly, yeah. So, and basically I left all the different colors to illustrate here. If you look here, also here, it's what the other parameters you leave fixed have little effect on the overall tendency downward here. But what we found interesting is it's really these background particles that react, but not the current sheet, and it's not sensitive. We tested that what exactly we define as the central current sheet. We varied that a bit. Now for the mass, the sensitivity to the mass ratio, it doesn't depend whether you separate or not. I couldn't tell by eye the difference between plots, but you see if we have realistic mass ratios, more energy goes to the ions. And just as Saltudi, there is a recent paper who looked at pair plasma and found that the non-thermal part of the spectra is interestingly similar, whether you do it 2D or 3D, which brings me to spectra, the last few minutes. So I told you the nice thing about this mass ratio is that we really can do longer simulations, and we do get a power law at all for the ions, which we can study. Whether this is then realistic or not is a question, but we would love to come up with some idea of how this spectra would behave if we go to more realistic mass ratios. So what's shown here is, for one case, a reduced mass ratio, some magnetization, no background fields, the electrons and the ion. We get a rather hard spectrum for the ions, for the electrons, a shallower one, softer one for the ions. If you have a guide field, you tend to have a harder electron spectra, which makes sense as the guide field allows you to stay longer in the acceleration region. If we then go to a realistic mass ratio, that's now only electron spectra. The ion spectra is not existing. We cannot integrate long enough. So we start to see with the background field going up even a very hard slope of p to the minus 0.5 in conventional units. And interesting, Cerruti et al. Found a similar slope for a pair plasma. And it's not only this, so we see really the gradual change as we increase the mass ratio, the magnetization, that this bump appears, and it's robust to what exactly we call background. Why it is there, that's future work. We don't know yet. And then last thing we looked at is how do the highest energy particles evolve? So what's shown here is the energy gain of the fastest particles as function of time, and we see different things. The dashed and the dotted lines, which are ions and electrons, are roughly the same in these units. So we can look only at ions. And remember, we don't see much of the ions, actually. It's also they're roughly straight lines, and that the slope of electrons and ions we did an analysis, it's really close to the 1-1 line. So we can look only at the ions in the next plot, and we can exploit systematic differences already seen here, kind of that's for different mass ratios. As you go to heavier mass, you gain the energy gain is slower. As you have a higher guide field, the energy gain is slower. And that's still a bit a mess, it's really work in progress. So with increasing mass ratio, if you connect again the blue dots or the green dots, with increasing mass ratios, the energy gain is slower. Same for a guide field. And good question, why? What we also looked at is who are these fastest particles? And that changes with time. So one particle may be fastest one at some point, and then another one takes over. That's what our data says. And for example, here we have the 5 finally at the end of the simulation fastest particle. And we track them back how they accelerated. So the 5 fastest in the end of the simulation at different tracks. Some accelerated continuously, others did nothing and then accelerated very rapidly. That's future work. We really have, that's only to make the point, we have the data along the particle trajectories at really high time resolution to hopefully look more into the physics. What are these particles experiencing in the simulation? And that brings me to the take-home messages. So one thing we see is that it's really, for some aspects, it really makes a difference whether you analyze the whole particle population you have or you look only at particles that have been far from your reconnection site initially. And we see that if you go to higher mass ratios, ions profit. They overall get more energies. And we hope to bring that into a better quantitative and hopefully physical insight to relate reduced mass simulations, which are still common in the literature for this problem, somewhat to the realistic regime. And yeah, many questions remain. Some we will not be able to address. 2D, 3D, we don't have that. Gamma max cutoff, we cannot integrate that long. Others like the very hard spectra or also plasmoid merging, we hope to analyze with the data we have. Thanks.
Okay, thank you. We have time for a couple of questions.
Do you see any, especially in the simulations with strong guide field, do you see any sign of temperature anisotropies, like parallel versus perpendicular, as I think he was discussing in the turbulent scenario?
Yeah, so in the augmented parameter space I showed focus now, I haven't analyzed that yet, but already Michael in his publications had quite some work devoted into analyzing that. So you find really quantitative information there. Yeah, we do see the anisotropy.
So temperature is higher in parallel direction?
Yeah.
Okay.
Yeah.
And I have a question as well about this energy partition, because if I understood correctly, you are studying kinetic energy partition, so the bulk flow acceleration. Is that, did you look by chance to thermal energy partitions? So do we heat more ions or electrons?
Not yet. We have the data to do that, but I didn't look at it yet.
Okay, thanks. And another question, maybe I didn't catch it. How you discriminate between background and current sheet?
Just geometrically. So on the onset of the simulation, if you will have current sheet is here, the inflows here. We say at initial time we chop here, and who's further out is background, and who's further in is current sheet. And we varied that cut quite some to check the sensitivities, and by and large, it doesn't matter too much.
Okay, thank you.
Any other questions? Maybe I can ask quickly while we set up for the next talk. So do you see any hint, any possible evidence of some trapping mechanism for those particles that are accelerating so fast?
You mean?
Like trapping in these, like in the islands generated by reconnection, for example.
We do see some of them getting, well, the center of the islands in this parameter regime is basically populated by particles that were initially close to the sheet center. But the accelerated particles we do see, they gather around the islands and get stuck there.
Yeah, I was wondering about the ones that initially are not really accelerating and then they have a big jump.
Could be. I mean, that's something I really would like to see whether they are accelerated. We also see, you've seen it in this plot where I showed how we do the time series analysis, that we do have merging plasmoids, so we get secondary connection. And we do have the data on this to tell whether these fast guys went where precisely did they get the speed. And I think that could be interesting.
Okay, okay, thank you. So let's thank Doris again. Okay, so the next talk is by Emanuele Sobacchi, who's going to talk about relativistic turbulence in AGN jets.
So today I'm going to talk about relativistic turbulence in jets from active galactic nuclei. So let me introduce a little bit the topic. This figure shows a beautiful multi-wavelength image of the supermassive black hole sitting at the center of the M87 galaxy. The black hole launches a relativistic jet which extends to distances of typically of 1 parsec, so this scale is 1 parsec. The bulk Lorentz factor of these blobs that you see here can be measured and is of the order of 10. So these jets are relativistic. According to widely accepted paradigm, relativistic jets extract their energy through electromagnetic stresses. So there are magnetic field lines anchored to the ergosphere of the black hole. Magnetic field lines are forced to rotate, and as the plasma flows outwards, it's accelerated. In order for this mechanism to work, the magnetic energy, the plasma close to the black hole here should be magnetically dominated. So the magnetic energy density should be much larger than the rest mass energy density of the plasma. The idea of magnetically dominated plasma is usually formalized by defining this magnetization parameter, sigma, which is equal to the ratio between the magnetic energy density, B squared, and the rest mass energy density of the particles, and MC squared. So magnetically dominated plasma, I mean regime where this sigma is much larger than unity. So this magnetization has the meaning of the available magnetic energy per particle. So simply by a conservation of energy, if the magnetic energy is dissipated, particles can be accelerated to ultra-relativistic Lorentz factors of the order of sigma. This cartoon shows the standard unification scheme of active galactic nuclei. There are many elements in this cartoon. I will not go through them. For what I'm interested in blazars, which are AGN that launch a jet, and the jet is directed towards the observer. So in blazars, the radiation from the jet is the strong relativistic beaming. So the important point is that radiation from the jet, if the jet points towards me, is so beamed due to the bulk relativistic motions of the plasma that it outshines, typically it outshines all the other components in this diagram. So in this sense, blazars are the ideal candidates, the ideal objects to study the dissipation of the magnetic energy that happens in the jet. This plot shows the typical spectral energy distribution of blazars. As you can see, the spectrum is clearly non-thermal. It extends from it has these two broad humps. It extends from the radio, 10 to the 9 hertz, up to the very hard gamma rays. So very basic question is how we think that the magnetic energy in the jet is eventually converted into the non-thermal radiation that we observe. And very general grounds, one may argue that the magnetic fields, which eventually carry most of the jet energy, which initially carry most of the jet energy, the magnetic fields are dissipated. The dissipation of the magnetic energy powers acceleration of non-thermal particles. These non-thermal particles cool down, and while cooling, they emit the non-thermal radiation that we observed that I was showing before. The cooling process here is relatively well understood, and the leading cooling processes are synchrotron radiation and inverse Compton radiation, and I will say a few more words in the next slide. The dissipation process is much less understood. I think, given the very large separation of scales, typically 8 orders of magnitude, between the transverse size of the jet and the kinetic scales, say in this case the particle Larmor radius. So since there is a huge separation of scales, I think turbulence is a very natural candidate to bring the magnetic energy down to the dissipation scale. We say a few words about synchrotron and inverse Compton radiation. So again, the spectrum has these two humps. The low energy hump is usually attributed to synchrotron radiation by a population of non-thermal electrons. Synchrotron radiation occurs when a particle gyrates in a magnetic field. So gyrating particle means that there is acceleration. An accelerated particle radiates. The typical frequency of the synchrotron photon is equal to the Lorentz factor of the particle, gamma square, times the non-relativistic Larmor frequency, which is proportional to the magnetic field, times the sine of the pitch angle. The pitch angle is the angle between the direction of the particle velocity and the local magnetic field. The synchrotron power is equal to the Thomson cross-section times the speed of light times UB, so B squared, the magnetic energy density, times gamma square, the Lorentz factor, square, times the sine square of the pitch angle. An important point, I think, is that in high-energy astrophysics, usually the pitch angle distribution is assumed to be isotropic. So typically, one assumes that the large majority of the emitting particles, of the emitting electrons, have large pitch angle. They move nearly perpendicular to the direction of the local magnetic field. And I will argue that this is maybe not the case, and this has important implications for the modeling of blazars. The high energy peak is produced by the same population of non-thermal electrons, and is usually attributed to inverse Compton radiation. So inverse Compton radiation occurs when a low energy photon, a seed photons, is scattered by a relativistic electron. The photon energy is conserved in the rest frame of the electron, and in the lab frame, the photon gains a factor of gamma square in energy. Gamma is the Lorentz factor of the electron. The power is similar to the synchrotron power. The only difference is that, so of course there is no pitch angle, and then the other difference is that the magnetic energy density is replaced by the radiation energy density. So in collisionless plasmas, magnetic energy dissipation can be studied through particle in cell simulations, and I don't have to introduce them here. An important point that I want to stress is this plot. So this plot shows the total power of the jet, which is inferred from typically from the large-scale radio lobes, versus the luminosity in the gamma rays. And one can see that a very large fraction of the jet power is converted into gamma rays. So this correlation, so this is very close to one-to-one correspondence. So this means that the radiative efficiency is very high, and we need to include the feedback of radiative cooling. So we need to include in the simulations the feedback of synchrotron due to synchrotron and inverse Compton losses. So here, particles are moved under the particles in the cells are moved under the effect of the Lorentz force, plus particles are cooling down self-consistently during the simulation. These two panels shows typical outcome of one of these simulations in the regime where sigma is, so the magnetization is much larger than unity. In this sense, turbulence is relativistic. The top panel shows the out of plane current density, and one can see the self-consistent formation of current sheets. the bottom panel of large-scale current sheets. The bottom panel shows the average Lorentz factor of the particles, and one can see that the energetic particles are located very close to the current sheets where most of the particles are energized. So here I show the typical, here I show the Lorentz factor versus time for a sample of particles, and one can see that particles get energized very quickly. They reach Lorentz factors of the order of sigma, and this sudden energization happens while the particle is in the current sheet. And then particles cool down due to synchrotron and inverse Compton radiation, and they cool down very quickly because I'm interested in conditions where cooling is quite efficient. An important point is that stochastic acceleration in this fast cooling regime is suppressed, so particles don't manage to get accelerated to Lorentz factors much larger than this sigma, because radiative losses are too fast compared to the time scale for stochastic acceleration. An important point is that here the reconnection electric field in these current sheets is not really aligned, but very close to the direction of the local magnetic field. And this imprints a strong anisotropy to the particle distribution, meaning that particles are accelerated preferentially along the direction of the magnetic field, or the pitch angle is much smaller than unity, or the parallel temperature is much larger than the perpendicular temperature, which was what Luca was showing the other day. Yeah. Is out of plane. So here the initial fluctuations are delta B. So delta B from which turbulence develops, the fluctuations from which turbulence develops are the same. I think in this simulation they are the same of the out of plane guide field. Then I will show cases where we change delta B over B. I will discuss later. So why I think this pitch angle anisotropy is important. So I remind you, the two peaks of the spectrum of blazars are produced by the same population of non-thermal electrons via synchrotron and inverse Compton. So since the electrons are the same, naively one would expect that the synchrotron and the inverse Compton light curves should be correlated. And actually, this is the case. So there is a good correlation in many cases. This is an example. So the black is the light curve in the gamma rays. So here, blue, green, and red are UV, optical, and infrared, so in this peak. And one can see that the inverse Compton peak and the light curve in the inverse Compton and in the synchrotron peaks show a reasonably good correlation. This is not always the case. There are the so-called orphan gamma ray flares where no correlation is seen. So this is the gamma ray light curve at energies larger than 0.1 GeV. There is a huge flare lasting 50 days. This is the optical light curve, and there is no flare. So this is very challenging because if the electrons are the same, it's difficult to understand why the gamma ray light flare should not have an optical counterpart. And here I think the pitch angle anisotropy is important. This shows the result of the simulation that I was showing. This is from the simulation that I was showing before. So the delta B, the fluctuation, turbulent fluctuation decays. They decay fast because the alpha velocity is close to the speed of light. Particles are accelerated. They radiate through synchrotron and inverse Compton. The red line shows the inverse Compton light curve. The black line shows the synchrotron light curves multiplied by a factor of 10 to the 3. So there is a huge suppression of the inverse Compton of the synchrotron light curve with respect to the inverse Compton, and this suppression is can be attributed to the pitch angle anisotropy. So I recall you, this is synchrotron power emitted by one particle. This is inverse Compton power. The ratio between the two is the ratio between magnetic and radiation energy density times the sine square of the pitch angle. In our simulation, magnetic and radiation energy density are the same, so the ratio is practically the sine square of the pitch angle. So this huge suppression is due to pitch angle anisotropy. So strongly anisotropic particles could produce these orphan gamma ray flares. Orphan gamma ray flares are the exception. Usually the synchrotron and the inverse Compton luminosities are comparable, so we need a mechanism for isotropizing the particle distribution. This plot shows synchrotron light curves, the dashed, and inverse Compton light curves, the solid, for different values of delta B over B, of the initial value of the fluctuation. So red is delta B over B square of 0.25, green is 1, and blue is 4. So as one can see, small values of delta B over B give very strong suppression, very small pitch angle, and very strong suppression of the synchrotron with respect to an inverse Compton luminosities, 3 orders of magnitude. Delta B over B of 2 give very small suppression. So I think pitch angle is quite sensitive on the initial conditions, and these variations of the pitch angle might explain this phenomenology with orphan flares and regular flares, which show or don't show a correlation. And finally, let me say a few more words on the, so one can do the exercise of fitting the spectrum, the 2 amps of the blazar spectrum, and infer the properties of the plasma from the emitting plasma from the spectrum. So doing this exercise and assuming that particles are isotropic, one typically gets a very small magnetic energy density, typically 10 to the minus 2. The magnetic energy density is 100 times smaller than the energy density of the electrons. And this is difficult to reconcile with the general idea that jets are launched as a magnetically dominated object through the Blanford-Nagek process. I think a possibility is that there is some residual pitch angle anisotropy. In any case, even if the pitch angle is not extremely small, the pitch angle anisotropy could solve this issue. So the synchrotron power is proportional to B squared times the sine square of the pitch angle. The inverse Compton is the synchrotron frequency is proportional to B times the sine of the pitch angle. So what we are actually measuring here, I think, is, so what we are actually measuring is B times the sine of the pitch angle. So there is no way to measure the component of the magnetic field parallel to the particle velocity. So I think eventually how this plot should be interpreted is that UB divided by UE times the sine square of the pitch angle is 10 to minus 2. So what we measure is B times the sine of the pitch angle. So I think a reasonable interpretation is that there is equipartition and that there is some pitch angle anisotropy, which leads to underestimating the true value of the magnetic field if the pitch angle anisotropy is neglected. So I leave here my conclusions, maybe, and I take questions.
Okay, let's thank the speaker. Are there any questions?
So the level of anisotropy in your particle energy distribution depends on delta B over B, right?
Yeah.
But I assume also the amplitude of the flare that you would expect over the average background will be a function of that, because that regulates how strong is your current sheet. So
yes.
is there an observed correlation between, let's say, the amplitude of flaring activity and the fact that you don't see orphan flare in certain JP?
Yeah, difficult to say. I don't know. I mean, maybe one could look into the data and check whether there is some correlation with the amplitude of the flare, flaring versus anisotropy. One problem is that it's not that frequent. I mean, sometimes they have simultaneous observations at multiple frequencies, but this is not that often. I mean,
but you do see some check. Is it possible to check something this in your simulation, for example?
In the simulations.
I mean, do you run them enough in order to see true flaring taking place?
Yes, the problem is that, so this is decaying turbulence, so typically there's one flare. Okay. I mean, and this depends on what you set in the beginning. So this delta, I changed the slide. This delta B over B is what you set in the beginning, so you have just one realization per simulation.
Yeah, nice. Go back to your last slide, the conclusion on pitch angle.
Sure.
So I've been hearing this for the past 5 years, and the one thing always bothers me, right? All peak simulation, yaws and hours, tiny.
Yeah.
I mean,
I agree.
extremely tiny.
I agree.
Yeah, that's right. So whatever mechanism that we want to maintain small pitch angle, when you try to imagine back in the real jet, I mean, there are all kinds of other processes that would try to isotropize the distribution.
Yes. So
and flare you can simulate, and you can simulate here is timescale is also very, very short. So you need multiple sites to go on at the same time in order to explain the total flare seen by whatever, right? So
I agree.
I didn't quite, I mean, I never understood how the pitch angle effect can be so strong that bring a factor of 100 in the UB over your energy. So I kind of want to hear your thoughts on that.
So, I mean, I agree that simulations are small compared to the 8 orders of magnitude of separation of scales that's in the real jet. I would say I'm maybe a little bit less worried about kinetic instability. So, for example, in this magnetically dominated regime, there is a range of instabilities that could isotropize the particle distribution but don't work. For example, Fyros, mirror, they all have a threshold and they don't work if most of the energy is in the magnetic field. There could be, so I'm say, another line of thought is that, I mean, maybe there is suppose that there is some process that manages to isotropize the particle distribution, should compare this process with the cooling time. So the time scale for this process should be compared with the cooling time of one particle. If cooling is fast, maybe it's a little bit less dangerous, but still the cooling time is much longer than the than 1 over the Larmor gyration time or something like this. So yes, there is a...
Okay, I guess we'll stop here. Otherwise, also lunch will cool down. So let's thank again all the speakers of this session. We'll be back here at 2:20 sharp after lunch. Thank you.
Insomma, il pitch angle è importante. Magari si studia sui libri, poi lo dice, ma no. Chi lo sa?
C'è scritto un articolo sul pitch angle, negli inizi della classe, credo non sa.
Lui qualcosa aveva fatto. Senti, ma il self-synchrotron Compton lo potresti aggiungere? Perché vedete...
nelle simulazioni di studio external Compton. Self-synchrotron è
sempre modellizzato in qualche modo.
Questo piano PC non l'ho detto, questo era tutto external Compton perché
dava come livello
dovrei sbracciare fotoni. In uno D forse lo puoi fare, ma
so che qualcosa stavano provando a fare
allora puoi fare sullo spettro medio, nel senso ti calcoli lo spettro di sincrotrone e poi dici vabbè quello non è quello locale ma è quello illuminato dai cubi vicini.
Comunque nel suo caso si riusciva sempre di più il sincrotrone.
Ma quella che in turbolenza è un po' grande quello. No.
Ma più che altro, diciamo, se prendi magneti radiation energetici uguali e stai picciando quel piccolo, alla fine puoi dire se il synchronous cooling è trascurabile.
E quando cominciano a esorbizzare.
In realtà non avevo neanche synchronous cooling, era solo cooling, però più o meno andava bene perché...
Ma quel cosa ci metti? Lavorantore?
In realtà solo un Vers Compton non particolarmente perché alla fine che è quello che avevamo qua, se è sincrono un pochino di più era solo in base.
Anche perché uno deve seguire il tracciato di calore bene. No, avevo fatto una
no, ma ho detto come prima mentre tu stavi sistemando
no, ma abbiamo fatto, cioè, in China non ci abbiamo mai lavorato, si va di continuo e sempre trovano fuori tutte le terze. No, io avevo fatto un modellino per gli acquisti della crowd, perché i nostri acquisti sono molto complicati, guarda, mi faccio questo della crowd, allora l'idea è che se tu in via generale che puoi avere la front side e il nostro back side per doppio il punto è che se vuoi che di tutto un anello è grosso così si richiede così di venire a valore di 0,95 C a meno che la distribuzione non fosse anisotropa. Nel qual caso l'emissione
cioè praticamente tu dici il bike con
pensi di fatto col fatto che sono particelle
anche noi in realtà cioè non ci sono questo già scritto una cosa sull'isotopia e cavo come sta prendendo senza cooling e si vede senza cooling si vede che queste sono l'assoluta si vede che il centro dipende dall'energia quindi ti cambia la
cambia anche quello
cambia la sloping di rispetto qui no perché si raffredda c'è un costante perché i fotoni vengono messi nella direzione del mondo quindi si raffredda più questo però nel radio della crowd del più perché se no si vedeva che il centro dipendeva dall'energia quindi però aveva scritto un articolo però in realtà la nebula non è visualizzata in media
non è tanto esatto però dove mettono le particelle
però le situazioni che tanto anisotopo sposta in una regione dove non è iniziata poi c'è tutta l'instabilità
Che la olla MHD suona 17 Hz, pura. Esatto. Poi se tu generi però del risultato
wave packages or whatever, and then you have the transfer to smaller scales. Also, this one would imply that there are ways of why they are concentrated only in structures and not somewhere else, and we are not really ways for that.
Hello, hello. Yes, it works.
se tu poi
Guardate che mi faccio da certo.
Matteo sono lui.
Hai visto? In effetti lui c'era neanche iscritto per l'ultimo, l'ho chiamato last minute. Tanto che c'è il treno alle 7.
Però fa parlare prima di me. Uguale.
Tanto non parla di... No, dai, ma ormai ho messo quello.
No, vabbè, no, non io se c'avessi il treno, c'avessi gente.
No.
Avrà caricato il mio computer? No, che palle. Perché la gente mi manda gli email? Non voglio gli email. Allora, Alicia Lopez Oramas, due postdoc con licenza d'acqua, no, postdoc licenza d'acqua. Che erano queste LS? Sì,
You are the first?
Yes.
Okay, good.
Are you chairing?
No.
I can chair myself.
I thought to speak, but then I wanted to listen to you. Okay, you are the first.
Oh, penso che devo fare, c'è un via senza mezzo, questa è la tenergia, la settimana che poi non posso io, perché posso io non può essere. Ma sai veramente convinto che puoi stare in bianco? Forse no.
Chiamo la gente. Vai, almeno questo. Te. Faccio io, deciso Massi. Te, Tripi.
La macchina di greggio sta arrivando.
So welcome everybody to the last session of the meeting. It's a pleasure to have here Luca Del Zanna from University of Florence. So I would really thank the organizers for inviting me. Sorry. I'm sharing my own talk because it's shorter. Yes. And I will ask questions to myself. Yes, even ask the questions, but not providing answers. Probably also because I'm not an expert in binary neutron star mergers. So this is, according to me, a really wonderful observation in 2017. So for the first time, we observed a gravitational wave event combined to photon information. So this is the merging of two neutron stars. This is the gravitational wave signal with the final merger of the two neutron stars. At the same time, well, actually 2 seconds apart from the merging, we also observed a short gamma ray burst, so photons. And after a while, a few hours or days, we could also see the optical spectra and light curves, which were changing in time, of course, evolving. Different wavelengths were triggered. So from optical, we also saw, well, X-rays, but later infrared and radio. So what is this event? So it's the merging of two neutron stars. Matter is involved this time, so no longer merging of black holes, which is only gravity.
Just out of curiosity, did you see neutrino in this event?
Neutrino, no, unfortunately not. Yes, for real multi-messaging, we also would like to see neutrino sooner or later. And a kind of nova was produced. It's called kilonova. This is something produced by the ejecta of the two neutron stars. So the material is neutron-rich, and there is radioactive decay powering this object. Well, I will concentrate actually on the possible amplification of magnetic field in such events, because to produce the powerful jets that are observed, because short gamma ray bursts are actually jets escaping from the material, you need powerful magnetic fields, like 10 to the 16 Gauss even. They have to be magnetically dominated somehow. Well, the dynamics should be governed by magnetic field. So of course you start with something that is the standard field of a neutron star from 10 to the 12 Gauss, which is already a lot, but not enough to produce such jets. So we have to amplify these magnetic fields somehow. Another issue which is not clear is so what happens to the merger? You produce something which is basically, let me show the next slide. So this is the in-spiral phase of the two neutron stars. Then they merge, and the two phases are clearly observed in the gravitational wave signals. Then you clearly see a jet, which is the short gamma ray burst, but you don't actually know what happens to the remnant. So does it collapse directly to a black hole, or there is a phase in which a hypermassive neutron star remnant is still alive and metastable, say. So for what I will be talking about now, I need at least that this is the situation. a few milliseconds of lifetime of a hypermassive neutron star. Here, millisecond is the time scale of these objects, because they are 10 kilometers object, the speeds are very high, so the millisecond is the natural time scale. So you need to amplify magnetic field to produce such jets. Maybe there could be even a really longer, much longer phase, up to 10 to the 5th second, in which this object can survive if the mass and the initial spin are within certain values, because you need strong rotation to avoid collapse. This situation can favor some observations of so-called X-ray plateaus in the light curves of X-rays, in which maybe a kind of magnetar, because if magnetic fields are so high, these are basically magnetars, and fast rotating objects through a relativistic wind can power this situation. So, so what does theory and simulation say? Already in phase B, you clearly have Kelvin-Helmholtz instability, because you have very, very strong shears of the two colliding objects, in which you can enhance your magnetic field. Then when the object is created, we suppose that that MRI, magnetic rotation instability, is very active and can further amplify the magnetic field. So in total, probably these are the factors from the initial magnetic field. If you want to go even beyond, probably you need something more. And this is the idea of mean field dynamo. So why mean field dynamo? Of course, dynamos is active when turbulence is active also in your 3D environment. But of course, in global simulations, it's almost impossible to resolve the small scales that you need, because you need well-developed turbulence, so you should be able to simulate both the large scales and the very, very small scales. So the idea of mean field dynamos is basically to mimic the action of this unresolved turbulence and providing a ponderomotive force which is able to amplify the magnetic field. So of course, mean field dynamo is the answer. I'm joking, because not everybody believes that the mean field dynamo is the natural explanation. Of course, it's a modelization of something that you cannot resolve. So how does it work? Well, most of you know, of course, the classical version that you can find in textbooks. The original idea, I think, was by Parker in the 50s. So you have a mean velocity field and a mean magnetic field plus fluctuations. If turbulence is established and you have a power spectrum, orders of magnitude, say, or decay in turbulence, and the fluctuations are correlated, when you do the average, a new term here can survive due to the averaging of velocity and magnetic field fluctuations that you can rewrite according to the underlying B field like this, something proportional to the B0 itself and something proportional to the curve of B, so basically the current, sorry. No. So basically you have, if you translate everything in your induction equation, you have the standard ideal term plus a new term here which is capable of generating, for example, if you are axisymmetric, a toroidal field out of a poloidal one and vice versa. Also, velocity can do this trick. Differential rotation can turn a poloidal field, again, in a toroidal field. And you have also an enhancement in basically the resistive term, not only the ohmic one, which is usually maybe negligible compared to this mean field term. So basically, it's like having an electric field which is the ideal one, usually 0 when you do ideal MHD, plus the resistive term, and a new term that you can call psi times B. Psi basically is this minus alpha dynamo. So, but in order to study BNS mergers or compact objects in general, you need to use relativistic MHD. So together with Niccolò Bucciantini, we thought, well, usually the condition in a relativistic plasma when you are ideal is to have the comoving electric field 0. We knew already that the resistive condition is this one, where J is now a comoving current, density current. We added simply this term because it's very similar to the classical case. So what is the effect? Well, on the sun, we know it already. So you can have a chain, for example, in the alpha omega diamond where differential rotation is important. Differential rotation makes a poloidal field turn into a toroidal one, but then the alpha term is capable of producing a poloidal one. The chain goes on, and this combined effect in the interior states of the sun are capable of producing the 11 years cycle of sunspots observed on the sun surface. So it's something periodical, but the period is not related, for example, to the rotation of the sun. It's something due to the microphysics or the turbulence properties. So we are basically injecting the same recipe in our GR MHD code. You have to translate everything in the 3+1 language, but the basic thing is this one. So first, we applied this dynamo to accretion disks. So this is not a BNS merger, of course. Accretion disk around Kerr black holes. For example, the same kind of simulations that are used for the Event Horizon Telescope observations. Well, not for the observation, but to compare the observation with the model. So you have a thick disk orbiting the black hole, and what you find in simulation, usually that you have jets, Poynting flux-dominated jets along the pole. Well, but in order to reproduce observation, people inject a magnetic field which is already substantially high. With our model based on dynamo, we can start with a very low magnetic field, and dynamo is efficient enough to produce the correct level of magnetization which is needed to observe basically the synchrotron radiation observation. This is a cut of a 3D simulation on the equatorial plane, and you can see this is toroidal magnetic field of different polarities, which is periodically produced by the converging islands of, like the sunspots converging towards the equator. We observed something very similar in disk. Well, the first one to do such thing is Matteo Bugli, who will talk as the last speaker here on a different subject now. And with my former student Tomei, we applied this to the EHD model. So, neutron stars. Neutron stars, well, we made a first attempt with Niccolò Bucciantini. This was a case in which you have to choose, of course, your profile of dynamo term. This is something that you give to the code. in this case was uniform and the star was static, so you don't have the differential rotation. This is a so-called alpha squared dynamo because you only have to rely on the alpha term. There is no rotation. But in any case, you can see the exponential amplification of magnetic field. And if lambda is the scale of the magnetic field variation, which is a fraction, say, of the total radius of the star, this is the growth rate that you are expecting, and more or less, this is what we find. So then we refined our model. The first attempt was, say, on neutron star, proto-neutron stars. So this is not the result of emerging. I will arrive to this basically at the end. And this model was based on this paper when there were reasons in which only the external layers of a neutron star were probably subject to the dynamo term, because in here you suppose that turbulence was more active due to this particular instability. But in any case, again, you select your profile for this psi, well, the alpha term, basically, and even if it's localized only in the external parts, you can see that both poloidal and toroidal magnetic field components can rise exponentially. These were kinematic simulations, so it means that you are only evolving for the electric and magnetic field while the structure is preserved, basically. So you need to include also a kind of quenching of this effect, otherwise the field will grow forever because there is no back reaction. Coming to BNS mergers, from 3D simulations of the real merger of two stars, you find that the structure is different from a standard neutron star in the sense that this is the rotation curve, so it's not with a maximum at the center and declining afterwards. You have a kind of central plateau, there is a peak, and then a kind of Keplerian decay. And so this is a kind of different situation. And what we did, we imported in our code the result of this 3D simulation. We are using instead of an axisymmetric simulation, but you can do this after averaging around the phi direction. And again, you find the same result. So dynamo still works, even starting with a small magnetic field, say 10 to the 10, 10 to the, no, probably 10 to the 11, and just in the toroidal component, but you can see that the alpha dynamo term is able to increase both of them exponentially. Everything depends on this kind of Reynolds number, basically. One is related to the alpha term, and the other is related to the profile of differential rotation. Again, you have to put some threshold if you are using kinematic simulations. Well, the last part of the work, so of course you cannot borrow every time a huge simulation from other people, so the idea was, okay, we have a tool to construct basically equilibria of neutron stars in general relativity, also updated with this kind of rotation profiles. You have to satisfy some Bernoulli equation, including rotation. So you can do it. You have a fluid equation, structure. You select some profile for your psi term. You can choose some also symmetry relations that you want to preserve. Well, once again, you start with some low magnetic field. You put some maximum that you want to reach. Again, exponential amplification. So we have a tool now to explore different possibilities for both the Xi profile, but also different equilibrium structures, say different rotation profiles. This is work in progress, so basically I've finished. The conclusions are that, well, you need huge magnetic fields to power the jet needed for short gamma ray bursts. So you need the jet is there, you need amplification of magnetic field. At the beginning, you certainly have these two contributions. They induce certainly turbulence. If turbulence is already there, you can hope that dynamo has an extra effect. Other people are doing something similar, different MHD closures with different terms, but basically the important ingredient is always this alpha term in the induction equation. Well, that's it. So this is where we applied this basically relativistic dynamo theory for disks around black holes in the papers here, proton-neutron stars, ambient S merger remnants. We are doing it now. And thank you very much. For, I think Bill was faster, but.
This sounds really interesting and probably fruitful. Are you putting the alpha beta dynamo equations as an add-on to your standard code for the global modeling? Or?
I'm adding these alpha and beta terms in the global code and equations. What I don't have is an equation for the evolution of alpha. Then I should, well, we should think to a, I don't know, a realistic model for such equations because it's not so easy. We haven't found anything in relativistic, say, simulations. Yeah.
Or else LES energy model where you actually have an equation for the evolution of the turbulence and then a formula that connects the turbulence to the alpha.
Yeah, yeah.
That's kind of what we do in Usmanov's global solar wind code. So I don't know if you want to take a look at what is happening there.
Yeah, we should see whether it can be translated somehow to the relativistic. Yes. Okay. Yes. Think.
Does this make any contribution to the photon opacity of through the magnetic photon splitting? And the reason I ask is I'm interested in the generation of very heavy elements, which is inferred from the opacity which comes in the light curve.
Yeah, certainly yes. It's not part, of course, of this kind of model, but if you want to reproduce the observations, yes, of course, yeah.
So in the omega profile you're using, is the flow actually stable without having an inflection point in omega?
I cannot see from these simulations because these are kinematic, but yes, they are, because this is the result of a real 3D simulation of merging, and there is a metastable phase in which this profile survives. So I don't know the theory, but in simulations, these are stable objects for a while, at least compared to the millisecond scale of everything. So it survives for longer. Rolf, maybe.
A question about energetics. So if you produce such high fields, how much you slow down?
I'll slow down. Yeah, certainly when we arrive to the threshold of that we put when the magnetic field is relevant for the whole dynamics, I expect also, yes, a slowdown, yes. But I cannot see from here because these were kinematic simulations, so the fluid structure was kept fixed. Okay, thanks Luca. Now we have Mattia. We have Giancarlo Mattia. Giancarlo Mattia is a new postdoc here.
Uh-huh. Sì. Sì, sì. Perfect. Hi everyone, I'm Giancarlo. I am a new postdoc here. My boss is Luca, who just spoke. Thank you, Luca. But today I'm trying to summarize some results I got during my PhD at the Max Planck Institute for Astronomy in Heidelberg. So, I mostly work with jets. Why are jets interesting? I don't know your idea, but mine is that jets actually span over order of magnitudes in length, time, energy scales. You find in very different astrophysical environments, so they're actually interesting astrophysical phenomena to investigate. And nowadays we came to quite clear understanding that you need mainly 3 ingredients to build a jet. You need an accreting object, which can be a protostellar object or an AGN, or also other possibilities. You need an accretion disk, and also you need a magnetic field whose strength and topology is favorable for launching and generating a jet. Now, through the years, many authors studied the properties between accretion disk, central object, and magnetic field, and the jet that is developing. But a question that I tried to investigate is how does the magnetic field that we need to build a jet is generated? So there are some possible origins, like we can assume that there's a central stellar magnetic field that then developed in strength topology favorable for jet launching, but I focused on the dynamo processes that can happen within the accretion disk because it seems a very general and ubiquitous phenomena that can happen both in protostellar objects and in AGN. Now, there are, as Luca also explained a bit, 2 types of dynamo simulations. So we can directly investigate the dynamo from the turbulence, so we can do some direct dynamo simulations, but then we would not be able to see the disk and the jet up to the large scales. So the approach that I adopted is the mean field dynamo. So we just assume to mimic the turbulence that develops in the accretion disk, and we just try to mimic the effect on the large scale. And then we actually can produce some simulation and some output that with the disk, with the jet, we can investigate the launching process, although we don't directly see the turbulence that happens in the accretion disk. The dynamo, as Luca showed also before, seems to be a very interesting process. Luca focused on neutron merger, but there are also other cases where they investigated the dynamo amplification of the magnetic field in the stellar context, in both thin and thick disks, in both non-relativistic and relativistic MHD context. So let's try to take a step back and let's try to ask ourselves, how can we build a good dynamo tensor? So we want the simulation to lead to a jet, and we want the dynamo to amplify the magnetic field. So we have to ask ourselves, how can we build a good dynamo model that actually is consistent with reality? Because we are not directly seeing the turbulence, so we have to try to develop a good representation of the effects of the turbulence. So we know that the dynamo, which is an additional term in the evolutionary equation for the magnetic field, is not necessarily isotropic, although it would be really easier, computationally speaking, if it was.
We know that it has some properties like a dependence on the midplane sound speed and a change of sign across the midplane. And since we don't directly see the turbulence, we cannot see the magnetic field killing the MRI in the accretion disk. So we need some feedback of the magnetic field on the dynamo, on the magnetic field, so on and so forth. The saturation of the magnetic field must happen, otherwise we have an endless amplification because this term is exponential. So some question that go in the direction of how do we develop a consistent model is like, how can we constrain the dynamo components? Well, one thing is that if the disk is thin, if we are in the thin disk approximation, the non-diagonal terms of the dynamo vanish. So that's already good enough, but can we do something for the other components of dynamos? How can we suppress the dynamo in presence of a large-scale magnetic field? And since also the diffusivity can be assumed to be triggered by the MRI in the accretion disks, how can we link the dynamo in the diffusivity process? So what we did was numerical simulation of jet launching by a non-isotropic accretion disk dynamo. So I used the Pluto code in 2D spherical coordinates. We started with an accretion disk surrounded by a hot corona, and as a starting point for the magnetic field, because we cannot create field from zero, we started with a very low radial magnetic field with a magnetization of roughly 10 to minus 5. And then we tried to build a more consistent dynamo model where the components are not forced or chosen by hand, but they descend from some mean field theory calculation. And then we also studied the feedback of the magnetic field on the dynamo. So, first step was to constrain the components. We worked with thin disks, so we can only care about the diagonal components. And in order to constrain them, we adopted the model of Rudiger with several authors, where basically the terms of the dynamo and the diffusivity can be all related to one single parameter, the Coriolis number, which roughly speaking means low Coriolis number, weak dynamo, high Coriolis number, strong dynamo. Now, can this model build a jet? Well, actually, yes. So we see that in the inner regions of the accretion disk, the magnetic field is amplified by some order of magnitudes from the very beginning. The magnetic field lines first start with a standard configuration for a tower jet, because we can see the magnetic loops that are threaded at different locations of the accretion disk. And then once the magnetic field lines open up, we have a standard blunt for pane. As the time goes, the magnetic field is diffused outwards, and the dynamo plays a role also in the outer regions of the disk, leading to an amplification of the magnetic field also in the outer regions. So we can safely say, yes, this dynamo model allows us to build a jet. Now, jets can be very different, and since we are trying to model the effects of the turbulence, we don't have one single recipe for one single dynamo model or value of the Coriolis number, sorry, that explains every jet. So what we did was a parameter study of the omega star of the Coriolis number. So we try to change the intensity and the strength of the dynamo to see if we can actually see some differences. So when the dynamo is very strong, we see some really smooth, opal field lines, a very continuous, very nice toroidal magnetic field. The amplification is pretty strong. We have a jet. We're actually very happy for it. What happens if we decrease the dynamo? Because of the anisotropy, different components of the dynamo now start playing a role. So what we see is the formation of anti-aligned magnetic loops within the accretion disk. And the point between these two lines, where the magnetic field line change polarity, are points where the dynamo is not that cannot amplify the magnetic field. We call these zones dynamo inefficient zone, and are able to affect very strongly the disk and jet dynamics. If we go even lower in the dynamo strength, then the dynamo cannot really amplify the magnetic field anymore. So we see that the magnetic field structure becomes much more messy. We don't have a smooth jet. We just have a slow, uncollimated wind. But would like to stress that strong alpha, stronger magnetic field amplification, as we expect, faster jet, everything seems really nice. But we still haven't figured out how to describe the suppression of the dynamo because of this large-scale order magnetic field. So since there's no clear univoc recipe, we tried different feedback strategies. For example, we tried a diffusive quenching where basically we don't suppress the dynamo, we just boost up the magnetic diffusivity until it counterbalances the dynamo effects. Then we tried a very standard quenching where the dynamo depends with the inverse of the magnetization. And since I'm trying to go toward a non-isotropic dynamo, why should the feedback strategy be a scalar? So we also try to adopt the non-isotropic feedback strategy of Rudiger 1993. And some questions we can ask ourselves are, how does the magnetic field saturate? Does it saturate at the same level? Does the disk magnetization change if we adopt different quenching strategy? But also, the topology of the magnetic field can be affected. And the main question results in, are the disk jet properties still maintained if we use different feedbacks? So, these are the simulation that I showed you in the previous plots, and so far nothing too strange. But then we tried another method. We tried the standard method, and we see that it somehow reaches lower magnetization. Why? Well, the answer lies in the feedback expression. So, with the diffusive quenching, we don't kill the dynamo, we don't suppress the dynamo, we just boost an effect that balances it. So the amplification of the magnetic field in principle is still there, it's just balanced by another physical process. How, while we apply more a feedback strategy that kills the dynamo, the amplification of the magnetic field at some point stops because the dynamo is truly suppressed. And when we try a non-isotropic model, we see that we reach even lower values of the magnetic energy. And this is because the dependence of the magnetic field on the dynamo is stronger. So the dynamo is suppressed earlier at a lower value of the magnetic field. However, although this is populated by different feedback models in different zones, we actually at least have a qualitative dependence on the disk magnetization and the jet speed, which is something that was found much earlier in the non-dynamo simulation. So we also want to see if we can actually retrieve this correlation. And yes, we actually do. So the feedback of the magnetic field on the dynamo, when we have only suppression of the dynamo, doesn't really alter this jet connection. But what happens if we try to link also the diffusivity? So the diffusivity is supposed also, in our context, is also supposed to be turbulent. So a large-scale order magnetic field should be able also to suppress the diffusivity. So on top of the tensor model that we adopted, and I showed you a video before, on top of the non-isotropic dynamo feedback model, we try also to adopt a non-isotropic diffusivity feedback where the diffusivity also has a strong dependence on the magnetization. So these are, as continuity with before, the simulation with the non-isotropic dynamo feedback model. Now let's put on top of that the simulation with this more consistent model where also the diffusivity is suppressed. What we see is that we don't have strong differences in the magnetic energy, but the dependence between the disk magnetization and the jet speed changes radically. The main reason is that we see a very strong collimation on the very beginning of the jet. The magnetic field saturates really quickly, and so and the jet is already starts developing very fast. So we believe that this may lie in the initial conditions, although we are not completely sure about it. We're still kind of investigating that. But magnetic energy seems similar. Well, in these two cases. In this case, it bounces up and down a bit. And the reason why this happens is that I hit a very strong point. Like, jets are not only like uniform plasma tubes. You see shocks, you see reconnections. So it's really nice to get a steady state for a jet model, and there are amazing simulations that do it. But we should also not forget that jets are not completely steady. They are not completely homogeneous. You see knots, you see stuff in there. So every time we see something that changes, we should also ask ourselves what is going on. Now, I have a video, but the video goes a bit fast, so I will try to describe it before. In this particular simulation, we see that at the outer regions of the disk, some magnetic loops are lifted up from the accretion disk, where they are able to reconnect. Because of the action of the dynamo and the diffusivity, the magnetic field polarity is reversed. Once they are lifted up and they reconnect, they lose some energy, and now there's nothing that really counteracts gravity. So these blobs of mixed material between the disk and corona are accreted until they shut down the jet. Once they shut down the jet, they really disrupted at the base of the disk. The disk changes magnetic field because of this injection from top of material. And because of the feedback, of the dynamo feedback model, the quenching is suppressed. The dynamo is restored, and then we see a very strong jet. Then the quenching is restored again, the dynamo is suppressed again, and we get a configuration similar of this let's say, flare. Now you see that the matter is going, shuts down the jet, very powerful jet related to an amplification of the magnetic energy. Then slowly the magnetic energy starts going back to its previous value because now the quenching is reacting again until we see something very similar to the beginning. And for people who looked at this line, then you see that it starts amplifying because something is happening outside again in the accretion disk. We actually see 4 of them. And we don't see more because at some point the accretion disk ends. So, in conclusion, it's very important to take care of how do we model dynamo and the diffusivity, at least in the accretion disk context, and different form can actually severely affect the outcome of our simulation. So, every time we try to add these type of processes, we should always care to be consistent. Otherwise, we may not grasp consistent results. Thank you very much. Yeah, you are the chair.
Thank you very much. I really don't know much about that. I thought this interesting with this diffusive quenching. Should we think of this a bit as in the form of like a anomalous resistivity? Is that kind of like what balances in your induction equation then, the alpha effect and the additional diffusion? Is that kind of what it does?
Yes. So, and we assume that these come from the MRI and the accretion disk. The diffusive quenching is related to the fact that if we assume that both come from the MRI, large-scale magnetic field kills the MRI. So we should also kill the diffusivity. And this is something that was not done before. That's why I stressed on it. Because usually what happens is that we assume that we used the alpha Shakura-Sinara prescription, and we assume that it has a certain dependence on the magnetization, which is usually m to 1/2. But then we don't, if you hypothetically had a very strong magnetization, then your diffusivity would rise up, like unconditionally. And so this is basically a method to prevent this amplification of the diffusivity as long as the magnetization increases. So, exactly.
So in this quenching process and then coming back at a stronger level, can it come back at a wide variety of different levels, such as produce scale invariant noise, like monograph noise?
So far, we're still investigating that because we also don't have so many because it depends on it's related to the finite size of the accretion disk. So this is, we see 4. And that is the second because it's the nicest to show. But if you then look at the full, like I showed only a portion of the domain, you see that there's something going on in in an outer part of the accretion disk. So we are planning to do higher resolution simulation in order actually to grasp that in more detail.
Another quick one. For these kind of extreme conditions, the pressures
The pressure doesn't change that much. We use, of course, a radial dependence and an angular dependence coming from solving these stationary MHD equations, but it doesn't seem to, like, there are some extreme conditions where the pressure is too low compared to magnetic one, and these can lead to numerical instabilities, but in all the simulations that we applied with this, there seem to be no issue. Yes, yes.
I guess what I'm saying is it possible that in these extreme conditions that the scalar pressure is no longer, can be no longer be maintained?
Yeah, yeah. I don't really know, but it can be.
Somehow that was possible. You could get maybe another electric field from that.
Yeah, indeed. We have not focused on that, though. Like, we assume that this can be, like, but our scalar pressure can be the same. I think there was Nicolo, and then, yeah.
So, when you compute your field coefficient or eta coefficient as a tensor, that typically should be done in the comoving frame, right? Because those equations are typically written in comoving coefficients.
Yeah.
So in those frames, the Coriolis is a term or whatever the gradient terms is the one that you would get from the transit coordinate if you put yourself on the word line and track, and not necessarily the one that you get from the global circulation of the system. So
Yeah.
is there any hint of how that can be managed?
Honestly, no. We basically, for that, we try to rely on the calculation that were performed before. On the other hand, we reach usually the values of the strength of the dynamo usually matches the previous simulations, so that was also gave us the hint that we could have done things more in continuity. Of course, there are possible ways to investigate more on that, but we try to rely on models that were already built instead of trying to develop our own mean field dynamo calculation.
Yes, it's a similar question. I'm imagining you're modifying in that equation.
Yep.
The actual terms. So if you look at the disk part, not the jet part, do you see anything different or similar to, say, real 3D disk?
Sorry? I didn't understand the last.
If you look at the disk part,
Yes.
you see B field developing.
Yeah.
As well. If you compare that part with, say, a 3D MRI simulation.
There are actually the difficulty is that to actually capture the magnetic energy, like in the accretion days, is a bit tricky, because I mean, if you want to do a global simulation, you don't really have the resolution. So there are currently some studies, for example, I think they're doing it with Athena, where they are trying to grasp, like to converge. But it's really hard because you need a really high resolution. When it comes to the more like the direct simulations, there's how can I say? There's quite convergence. There are some studies from Gressel that actually try to relate the kinetic, so the Schirmbach simulations with our large scale, and there seem to be decent, quite good agreement. No, their treatment are then the average of the large scale coefficients are similar to what we adopt.
In the flares that you were mentioning, like the time scales, what are the relevant time scales? And I mean, can you quantify it, or are they related to the properties of the dynamo, which you don't already know?
They are actually related to the properties of the central object. Like if you have Since our simulations are non-dimensional, if you have a protostellar central object and you have an AGN, of course it changes. They are. Yeah, so what we see is that the time scale for that is of the order of years, for example, a protostellar object. But that can also depend, I mean, we are also expect that to depend also, we are trying to do also higher resolution simulations because that may also depend on the resolution of our system, but still is not a spurious effect. But it can, maybe the time scale of that can converge like once we have actually more resolution where the field changes polarity. It happens when we add the feedback on the diffusivity. So if we don't add the feedback on the diffusivity, it doesn't show up. Yep, sorry.
Good afternoon. So with his work together with Doris, who spoke before, and Mark Dickman in Sweden, and I would like to thank the agencies for support. So the whole talk is in the context of microquasars, and here is just a small computation what a microquasar is. So we have a secondary star here on an accreting black hole, and as the stars orbit, the wind of a secondary star gets turned around and is shaped in a spiral. This is like in the sun, the co-rotating interaction zones. And then if you zoom in into the black hole, you see there is an accretion disk forming, first highly not spherical, but on a very small scale it becomes spherical. So this is the context. I would like to point to two important numbers. If you accrete onto a black hole, you can get up to 6% of the rest mass of a particle. And in the extremum, if you accrete to a fast rotating Kerr black hole, you can gain up to 42% of the rest mass of a particle. And if you have an accretion rate of this order, then you will gain 10 to the 40 to 10 to the 37 ergs per second. So this is the energy scale. The energy then is distributed to different components. So certainly the kinetic and thermal energy of the flow. But of course you have emission, and you will eventually drive a jet. And as we just heard, you may amplify the field to very high. And this was also the background of the question before, because if you have this kind of energy gain, it's very hard for protons to have a field which is relativistic. So the regime is certainly relativistic for the electrons, but not necessarily for the protons. If you want to have relativistic fields for the protons, then you need to have a reservoir, a local reservoir from where you can tap energy. On the other hand, you will certainly create pairs. Okay, why jets are interesting in the context? Well, I like jet from the fluid dynamic point of view, but of course, they also help to solve the accretion angular momentum problem. And depending on how much energy is in the jet, you may have less energy in other channels. So I think it's a key to understand black hole accretion. Another point is jets also significantly contribute to observed emission. So this is also this morning we heard that, and also this afternoon. In this particular model of Kansas, you see the emission in the X-ray from the accretion disk, but the green here is in the optical emission by synchrotron radiation in the jet, in the optically thick regime, which is probably here, and then we have a branch of the optically thin regime in the from synchrotron radiation in the jet. Okay, and the third important point is heavy particle acceleration in the jet. And this question becomes more interesting again because recently it was mentioned that there is a tension in the supernova remnant paradigm for particle acceleration just beyond the knee here. And this because in young supernova remnants there is just a lack of TeV photons. And TeV photons must be present if you accelerate particles to wet energy. So the paradigm is that the highest cosmic ray particles are accelerated in jets of HENs. So it may well be possible that the tension could be resolved by contribution from microquasars near the knee. And there are such models here for Cygnus X1. This is just a hadronic channel of particle acceleration and associated photon emission. And this becomes now into reach to be observed. So in the next few years, it's perhaps possible to verify or falsify this idea. Okay, so hydrodynamical simulations, I should say this model here is of course an ad hoc model from just a sketch. Now we have decided to make a numerical model, a large scale model from say 10 to the 8 gravitational radius down to the horizon. And I don't feel that I don't want to make a metaverse out of that, like other people, but I would have a reliable model where I can check dependencies and mutual interaction over scales. And then if we are interested in a particular thing is we just zoom in and have there a big simulation to anyway, if you now in this spirally shaped environment look at the plane normal to the orbit, then the space is structured in such shells, and if you shoot the jet in, this is done here manually, not in the fashion the speaker before has shown. When we see it interacting with these shells, with this temperature and with this free emission, you see spots of more of high emission and where the jet hits the shell. If you look more close to the black hole, so the black hole is here and the jet propagates from here. When you and the companion star sheds his wind from here, when about this area will be accreted, and we see a bow shock around the jet, which helps to extend a little bit the accretion region, but all material above or below will be lost to the system. And again, we can then look at inverse Compton and free emission, and you see important differences. Of course, free emission is more, it depends quadratically on the density, so it comes from dense shell, whereas the inverse Compton of stellar photons are more in the field. Unfortunately, so far we have no spectral decomposition. It's just the integral of the emission, but I hope to show you soon some spectra. So if you look closer to the jet, then of course, if you do a higher resolution simulation of the jet, you see instabilities, mostly originating in the shear, but also by other processes like Rayleigh-Taylor or magnetic instabilities. And this means that the jet is steadily heated by dissipation, and we have a mixing of jet and ambient material. Both is important to for two reasons. First, these models of Kansas really need heating within the jet to be able to reproduce the spectrum. And second, if the jet is really starting in the vicinity of the black hole as a pair jet, then to be able to have proton acceleration in the jet, you need to mix in protons. However, of course, we encounter the same difficulty as everybody. If you look at numbers, the gravitational radius in this particular case of signal 6-1 is about 23 kilometers. The jet width is at the base maybe 10 gravitational radii or even more. The inner accretion disk radius is between 6 and 100, say, depending whether we have arrested disks or disks really going till the last stable orbit. And if you have the mean free path between two strong impact collisions of particles, we have some gravitational radii. This is the scale. So the dynamics of the vicinity of black hole is clearly sub-MHD. However, the mean free path is not so extraordinarily big that we don't have collisions. And we would like to have collisions if we would have particle acceleration and interaction of protons. And this is relatively similar for temporal. The kinetic scales are just much, much faster. So that's why we tried to look at some aspects of the jet in the kinetic regime by means of peak simulation. And so we constructed a little model. So this is really the work of Mark Dickmann with a little bit help of us. But we want to answer, can a pair jet push away the ambient plasma? Or to what degree protons are mixed in? And what is the spatial scale of the interface between the two components? So we take a uniform electron-proton plasma, at rest, mildly magnetized, and we shoot a non-magnetized pair jet into this ambient region. I should say there are 5 cases. So the 1D case, and then you can, or if you go to 2D, you can orient your magnetic field in the different, in different directions, and then you can go to 3D. One word about this interface here shown in black. So the interface pushes away the ambient plasma, which is at rest. So it must accelerate ambient protons and electrons, and it must decelerate the pairs of the jet. So this is a non-ideal interface. It has a width which is at least some inertial length of electrons. If this is an electric process or a gyro of electrons, if magnetic field plays a major role, or if protons play a major role, this is the width of the interface is several inertial lengths of protons. And since we have a lighter fluid pushing away a heavier one, the interface should be Rayleigh-Taylor unstable. So we are going to the 1D case, and now in the same figure, you see the process with 2 slightly different parameters. So for simplicity, just look at the right half of the picture. But what you see is you shoot at time 0, you begin to shoot in pairs, and then these are the electrons of the pair plasma, and these are the positrons of the pair plasma, and these are the protons of the ambient plasma. And what you see is more or less this pair plasma stays well confined, and the protons don't penetrate into the jet. And the reason is we have a magnetic structure, electromagnetic structure, which helps to prevent that, and this structure looks like that. You have the ambient electrons, and you have these are the jet positrons, these are the jet electrons, and these are the ambient protons. And just in front, sort of the interface, center of the interface is about here, and just before, just behind the protons is a big magnetic wall, which is created by pushing away the ambient magnetic field, and this helps to really separate the two phases. We call that electromagnetic pulse. So if you go then to do the ondular mode, where the magnetic field is in this direction, in the horizontal direction, and the jet pushes from top to bottom. Initially, Rayleigh-Taylor instability grows, but eventually this Rayleigh-Taylor instability is stabilized by the horizontal magnetic field. And essentially, the interface between the two phases is thin, 2 or 3 electron inertial lengths. And this will stay forever. And this is very similar to MHD, where ondular mode is suppressed, strongly suppressed in the Rayleigh-Taylor instability. This is clear. If you start to bend the magnetic field, you feel the magnetic stresses, and this suppresses. So essentially, also here, no mixing. If you go to the interchange mode, where now the magnetic field is in this direction, you start to see we still have relatively combined jet, and not a lot of protons penetrate the jet, but the interface is much more widened. And if you look at magnetic structures and protons are now organized as fingered islands. You have magnetic structures which are formed by many flux tubes. And so this is, of course, then a possibility to dissipate by reconnection. Still, as I said, no real protons in the jet, and not really a lot of pair outside. In 3D, and this is very, very preliminary, situations start to change. The interface now is really thick, several ion inertial lengths. Again, magnetic field, which is this, I think, is organized in flux tubes. And now we have some mixing into the jet of protons, but also from magnetic field, which is interesting if we would like to have some heating in the beam. But this is very preliminary. Okay, so the conclusions, microquasars are relativistic multiscale multiphysics objects. And to study them, we propose to have two different approaches: full-scale simulations to check interdependencies and interactions, and then we can put ad hoc models on firmer ground. But on the other hand, the kinetic process need to be studied as well. Otherwise, we are not quite sure what these hydrodynamical simulations are on very firm ground. Thanks.
Thank you very much. If I remember correctly, some of these microquasars can be pretty loud radio sources, right? Is that like gyrosynchrotron radiation or something in the jet? Is that important in the overall energy budget of this, or would you say
No.
you showed some radiated processes, right?
In the energy budget, yes, in the sense that they are coolant. So, the more difficult part is how we overcome the cooling, because we clearly need a super adiabatic temperature profile. So for that, it's so much important that we have dissipation in the jet, which refurnish the temperature.
But the peak code, if it's relativistic, would also create that, right?
The peak code is relativistic, but at this point we have not included any cooling.
Are you expecting the same figures that you were observing in 2D? They were less evident, but probably.
Yeah. So I don't know. I have gotten that picture 2 days ago, but it seems that we have flux ropes and some elongated islands of the protons, but much more analysis is really needed to understand exactly what is going on.
No? Spero bene. Con questo ho assorto la gente. Allora, sì. Vediamo un attimino. Okay, so yeah, you can read the topic here. And just for those of you who are not very familiar with the fields, a brief introduction. So, neutron star is basically relativistic conductor with a very strong magnetic field and rapid rotation. And when you tell things like this, it looks like it's an exercise for the Jackson book that every student should be able to solve, and instead is a 40-year-old plasma theorist has been able to make out anything reasonable out of it. So the key idea is that out of the rotation and the magnetic field you can create a very strong electric field at the surface. The field at the surface is so strong that it basically can pull out electrons from the very surface of the stars. In some circumstances, can even pull out ions from the lattice and accelerate to very high speeds. Now, there are highly nonlinear phenomena that appears in the magnetosphere of the pulsars. Because particle moves along curved magnetic field line, they produce curvature photons. These photons propagate to a magnetic field that's so strong that they basically get percreation in the magnetic field, and you have a percreation cascade. So ultimately, out of any electron that you manage to pull out from the surface, you can produce, at the other edge of the magnetospheres, around 10 to the 5, 10 to the 6 secondary pair electron positrons. And you end up with a very strong wind. So basically, these are relativistic accelerators that produce winds with Lorentz factor that are estimated in the range between 10 to the 4 and 10 to the 6. The other aspect that's quite important for the specific argument I'm discussing is that pulsars are born in very violent event. The neutron stars, the supernova explosions are typically the most violent event after the Big Bang in the universe. If you look carefully what is the level of momentum anisotropies that can happen in the core of a massive star is such that despite the neutron star being an object of about 1.4 solar mass, it can receive an efficient kick, and typically neutron stars have a velocity that are in the range between, there is a low velocity populations, but typically of order 400 kilometers per second. They are the fastest stellar population in the galaxy, just because of that. So the end result is that you have a very active and efficient wind producer, wind blower, that moves very fast. Now, these objects are born within a supernova remnant. Yeah?
If you go back one slide, so
Sorry, it was this.
Of course, this wind is neutral, so you first get the electron out, and then you put the proton
So basically what you do, you force electrons out, and electrons pair creates, so you get positrons, and positrons flies in. And you can get essentially, you can pull electrons and even a small amount of ions if you want. But you manage to get the things, the charge neutrality is preserved because you have pair creation in the magnetosphere. So you basically self-regulate out of that.
But protons to get out, or is unintelligible?
Depends. Protons can get out too, in principle. It's not clear how many protons are in the wind, if they are a sizable fraction of the energetics or not. But there might potentially be protons. Ions, actually, if you think of it, because there can be ions that get pulled out of the surface.
Just to make a note, the proper motion convention in the 400, 500 kilometers per second, that's due to this asymmetric collapsing in neutrino coming out from more...
It depends. So it's not clear what is the reason. So there are possible things is that if you are born in a binary system, which is likely because these objects comes from massive stars and there is a high binarity fraction in massive stars, then the binary disruption can lead to high kick speed by itself because you are removing mass. There are other two options. One is, as you say, that during the formation of the proto-neutron stars, the neutrino emission might not be isotropic. And there is another possibility related to the fact that the very collapse and the first phase are highly unstable. This is SASI mode instability that basically is the accretion shock. So actually is the gravitational pull of the surrounding envelope of the stars that plunging down, not in a uniform way, that shuffle the stars. So you have still tens solar masses of stuff around you that can pull around. So typically there are various, there is not, I think, a single mechanism that explains all, but there are many reasons to explain this high velocity speed. So typically what happens is that you form there inside supernova remnant, and they spend the early lifetime inside the parent supernova remnant. But because of their speed, and because the supernova remnant is bound to slow down as time passes, this object will finally escape the systems. You see here a few cases where the pulsar is actually moving through the supernova remnant. And typically, if you take typical evolutionary model for supernova remnant and the typical speed of the pulsar, you expect the pulsar to emerge out of the supernova remnant and begin to interact with the ISM when the pulsar is about 30 to 50 kiloyears old. And the point is that this is much smaller than the typical active age of the pulsar. So the pulsar is still producing wind efficiently, producing radio emissions, and the typical energetics of the pulsar in this phase is of order 10 to the 36, 10 to the 34 per second. It's quite intense. Once they emerge out of the supernova remnant, they start interacting directly with the ISM, and basically they do exactly what the sun is doing. They blow a wind, they move through the ISM, they are highly supersonic, and so they form a bow shock with the relative tails that maps, is the relativistic equivalent of the heliosphere, if you want. With the difference with respect to the heliospheres that we look at the heliosphere from the inside and we look at this object from the outside. So it's convenient to look at things from outside down. So here are two examples of objects, and what you can see here is basically this green stuff that you see here, as well as the red shades here, are actually H alpha. So these are moving through neutral hydrogens. Neutral hydrogens are going through the forward shock. They are doing charge exchange process and ionization process and produce H alpha. So this basically traces the neutrals. The red stuff that you see here is X-ray. These are non-thermal emissions from particles coming from the pulsar. It's electron-positron pair that are somehow accelerated at the termination shock of the wind. That's where it is supposed to be accelerated. So if you look there carefully, you have something like this, essentially. They map this structure, and you can tell the region that characterizes the pulsar wind and the shocked ISM. Now, this is a sample of all of these objects, and you see there is a very, very vast variety of structure. There are systems that have a very elongated tails, brighter, some have a conical shape, some others kind of these mushroom plus tail shapes. So there is, depending on how the interaction happens, you can have lots of different morphology. And this different morphology ultimately should actually depend not much on the condition on the ISM. The typical coherent scale of the ISM are much larger than the size of this object, should actually trace the properties of the pulsar wind, essentially. So these are a map of the energy distribution in the pulsar wind. So what we have been doing in the past is try to model these objects. This is a very simplified picture of what we are doing. So we have our pulsar here is producing a wind. Now, the wind is characterized essentially by two parameters, these dynamics. One is the kick velocity of the pulsar. You have a magnetic field in the ISM, which does matter for example, particle escapes, and if you want to understand, for example, reconnection at the contact discontinuity. And the other things that matters a lot is the inclination of the pulsar spin axis, so the magnetic field structure of the wind with respect to the kick velocity. So this is intrinsically a three-dimensional problem. If you try to solve in 2D, you get a rough idea, but basically you don't get the correct magnetic geometry that sits in there. If you don't get the correct magnetic geometry, transporting particle, figuring out what turbulence and reconnection is doing is quite complex. So in this case, what we have is a pulsar that sits here, is moving upward. The pulsar is rotating, and the rotation axis is actually inclined 45 degrees. And as a consequence, the pulsar wind is stronger in the equatorial plane. This is a typical structure of the pulsar wind. There's a higher luminosity, and is weaker on the polar direction. So because the wind is highly anisotropic, as you can see, there is an enormous level of turbulence that gets triggered in the tail. So the flow downstream here is highly turbulent. Now, you might imagine that the level of turbulence and magnetic mixing, this is a density map, would depend actually on the structure of the wind. So you can repeat this toy, and you can look, for example, at things like the luminosity. This is the speed, for example. This is the relativistic speeds, and you can see that as you go into the tails, there are part of the tails where the speed is quite small. Basically, it's kind of cavitation regions, if you want. And there are portions of the tails which instead the speed reach much faster, and you get to fraction of the speed of light, basically. And this is the structure instead of the magnetic field. Now, if you look carefully here, you will see these are the typical current sheet that forms in the pulsar wind, and they do survive a little bit even in the downstreams. Not much in these kinds of simulation because of the level of anisotropies, and this is a low magnetization wind, so the turbulence managed to destroy almost everything. Now, things changes depending on the level of turbulence and the structure of the anisotropy of the wind. So these are essentially the same systems at two different levels of magnetization. This is a lowly magnetized isotropic wind and anisotropic wind. Low magnetization sits on this side, on the left, high magnetization on the right. So if you have a highly magnetized structure with an isotropic wind, you do see that the structure in the tails is very laminar. And then in other results, you do see that current sheet managed to survive all the way in the tail. So you get memory of the injection in the head very far away. If you have a low magnetization wind or a wind highly anisotropic, basically you end up mixing everything and losing memory of your injection. So the typical speed at which they move through the typical speed in the tails is the fraction of the speed of light, 0.5 c. The turbulence is still subsonic in this case. This is a relativistic system, so everything is moving at a fraction of the speed of light at the end of the day. So the speed at which this thing flows out is much bigger than the 500 kilometers per second. So ultimately, you will have to somehow reach equipartitions, but that's happened on a very long time scale. We see tails that are parsec long, a few parsec long. So they really manage it. It's, if you want to say that, yes, because this is a sigma 1, so it's not even a high, is that the equivalent of a low beta, probably, I can't remember which way it goes, a highly magnetization, so the magnetic field stabilizes a lot and act against the developing of turbulence, essentially. And if you look carefully, this is an image, this is a cut in the tail, and you can clearly see that the polarities of the magnetic field are preserved on large scale in these kinds of models, and in these models, instead, the polarity are quite mixed, so you do have really turbulence. You can even look at the zoom. If you zoom a fraction of the tails, you can see clearly the difference. And if you compute the structure function, you will see immediately that these two not even map to each other. So the good point is that in this high magnetization case, the interesting thing is that you do see that current sheet survives. The polar current sheet and the equatorial current sheet. And if you take a cut anywhere, even far away from the injection region, you do still see them. So what happens is that basically the fluid is well separated. What you produce in one hemisphere stays in one region, what you produce in the other hemisphere stays in the other region. What we produce in the polar regions flows in a certain direction and not. So in a certain sense, in the absence of turbulence, the tail maps quite well the injection. So depending on how you accelerate particle here, you can map it to different region in this, as long as they do not diffuse too much, which means the low energy and low Larmor radius things. You can look at the emissions that are different in the structure of the emission from the turbulent case to the non-turbulent one. And this can explain, for example, why in some systems you do see a brighter tails and a fainter head, and in other systems you see the head is much brighter than the tail. It's an indication of this. So the most interesting things that we have about this object recently is the fact that these objects show X-ray emission, some of them, where there should be none. So if you have this, yes? We do. We see reconnection. So the problem is that the code doesn't have a resistivity. So whatever happens is numeric, but there are places where we do see reconnection. Now, the point where we do see reconnection is actually mostly in the boundary between the ISM magnetic field that go through the shock, at the magnetoposer, if you want to call it in some sense. That is where we see most, and that depends on the polarity. So there are, depending on the inclination of the system. Yes. This is the numeric. No, we cannot, we do not resolve. In principle, so this is okay, I'm going to show you. This is an AMR, okay? So if you look how thin the thing is, it tries the resolution. So get larger here just because the resolution is smaller than here. So we do not control the effective size of these things. Okay, so these are what puzzles most about this object, and the fact that we do see emission where there should be none. So if you take the simulation, you find everything's going on the back, on the tail. So if you take an object like this, you see the H alpha shock is here. So okay, the tail is in this direction, everything should flow here, and you see X-ray particle in this direction, like 90 degrees out of it. So there are many indications that somehow X-ray emitting particle, or TVA, high energy emitting particle, manage to escape out of these systems. And they do not just escape because somewhere in the tail they manage to spread out of the fuse. They manage to escape from the very head where they are injected.
That's the direction that the polar wind has, that the pulsar wind has the highest speed, right?
So this is the pulsar wind, the pulsar is moving in this direction through the ISM. So in principle, you would expect matter to go backward. You don't know what it is because you don't know the axis of the pulsar. It's very complicated to measure the pulsar inclination axis. You can do it with radio polarimetry if you believe it, the rotating vector model, which no one believes it. But the point is that this is not, this is not the jet from the pulsar wind. If I inject a jet in my system, if I try to place a jet there, because of the interaction with the ISM, it doesn't punch through. The energetics is not enough to have a jet that streams out.
In the graph, you see the small jet inside. This is where.
So if I go back here, if I take this simulation, for example, okay, this one, if I fire a jet in this direction, it will get a little bit bump here, and that's it. Everything will go back. Essentially, because you have a run pressure equilibrium, and the jet, it cannot carry 100% of the energy of the pulsar, and even if it does, it will be still bent backward, essentially. The energetics in the X-ray is typically 10 to the minus 3, 10 to the minus 2 of the spin down of the pulsar in these features. So the energetics is it's weak, right? They don't carry much of the power of the pulsar. That's for sure. They don't get to 100%. Sorry, I got screwed up. Okay.
I have a question that is very easy. So you say it's almost 90 degrees, but this is the plane of the sky.
Yeah, so the point is this, okay, yes, it's true, but consider this. The pulsar is moving, because this is a very fast pulsar, 800 kilometers per second. So if you want to make it also out of the plane of the sky, so things get even worse, because you have to assume it's even faster. You are already on the tail of the distribution. So it's not impossible, but it becomes complicated. And the other issue is that this is a very long feature. It's a parsec long, so if you incline it, it gets even longer. So in principle, there's nothing against it. You have one or two features, but then you screwed up the energetics. Because the point is this, you can estimate how much energy is here based on the standard equipartition model. Now you need a volume for that, right? And as more you incline in this direction, the larger is the volume because there is a sin I things. So if that sin I things gets closer to 90 degrees, your volume explodes and you run out of the energetics necessary to do these things. Now, issue with this object are two. One, how particles manage to escape, why they do escapes in these directions. These are all one-sided jet. There is a little hint of a jet on the other side, but it's very faint. But the other issue is how do you make these things shine? Because this is ISM. The magnetic field in the ISM is very weak. And if you want to make these things shine, you need to raise the magnetic field to about 20, 30 microgauss, which is about a factor 10 higher than the magnetic field in the ISM. You have similar issue, for example, here. This is the Geminga halo. This is a high-energy halo that's seen in TeV. The problem there is that if you take the magnetic field of the ISM with its turbulence and you try to put particles there, you don't make an halo. They just escape away. So if you want to confine the particle there, you have to increase the level of turbulence, which means, again, the magnetic field, the unperturbed ISM magnetic field model won't work very efficiently. So just to show you a kind of other examples of these objects, you do see systems where you have a very high level of polarizations, systems where it's bright ahead. So we have investigated the problem of a particle escape. So these are a set of objects. So just to show you a few examples, you can see that typically this is the luminosity in keV and the length. The length goes from some few parsecs to even 11 parsec in the case of the lighthouse. So these are a very long structure. The other things to notice is that some of them are very straight. Even in the guitars it's very straight. And some of them instead show some kind of bendings. And in general there is a correlation between the length and the presence of bending, and I will return on this point at the end. No, they're only seen in X-ray, and they're not seen in radio. In radio, there's a big issue looking things in radio, and for two reasons. First, that typically in radio you have a very crowded field. So these are very faint objects and very narrow, which means that for radio is a mess, because if you want narrow things, you would like to have interferometry to pick them up. If they are very faint with interferometry, you are screwed up because it's very hard to get luminosity. So ideally, you would like a combination of single dish and interferometry to act together, but I don't think it has ever been done. So there is also good reason, so the theory that for this not to shine in radio. Because in radio, you need much lower energy particles. And it's easier to have a high energy particle escape from systems than low energy particles. So you can take a model. This is a simplified model, so one of our bow shock. You do see there is a polar current sheet that flies here. There is the equatorial current sheet. So what we've tried to do is what happens if you inject particle at the termination shock, and if you inject high energy particles. Now, high energy particles, by definition, are particles that have Larmor radii comparable with the size of the termination shock. You can't make higher energy particles simply because you cannot confine them into the systems. So if you do that, what you find is that this is the magnetic field in the ISM. And you find that essentially the magnetopose changes. There is a size, because of the geometry, where the field of the ISM and the field of, if you want the heliosphere, are aligned. So you do not have effectively a magnetopose or a current sheet. While on the other side, you do have opposite polarity, and as you expect from opposite polarity, you will have reconnection there. So ultimately, reconnection is on one side. It tend to happen on one side of your bow shock, which will explain why particles tend to be, the escape tend to be one side. So you have systems like that. You have particles that float. The reconnection site is more or less here, I can tell you. And what happens is that if you inject particles, these are particles that follow the Larmor radii. What happens is that particles tend to get confined within current sheet. So depending on the sign, essentially the current sheet makes particle mirroring through them. There is no average, there is no guiding field in this simulation. So the current sheet are neutral current sheet. The pulsar wind works that way. And the end result is that when they reach the place where reconnection becomes efficient, they can jump on magnetic field line of the ISM and escape out of the system. So if you look at that, that's what happens. You take your model, you inject particles, and depending where you inject them, you can have escape or not. So these are particles injected on the back, which manage to stay confined in the tail. They don't manage to escape. The particle that preferentially escapes are the one injected in the front sides that moves in the so-called polar current regions, the one that typically reconnect. And the other issue that you see are two things. The escape is different between different charges, just because current sheet selected the charge that they manage to confine. And it's asymmetric from the left and the right, because essentially reconnections select one side of the Bausch. So what you finally have, you have essentially one side of the charge-separated current that emerge out of the system. And this is quite important because the charge-separated current can trigger instability in a different way than flow of charge-neutral particles, essentially. They are more efficient in triggering that. So this is an example of what happens if you change the energy of the particle. So if you take particle at the maximum possible energy that's achievable in these systems, Lorentz factor of order 10 to the 8, you see that almost all of them manage to escape. And they escape out in a fashion that's very reminiscent of diffusion. As you lower the Lorentz factor and you go down to around 5, 10 to the 6, basically the flow of particles is far more asymmetric, but is also far more reduced. And you get a change from diffusive emission to escape due to reconnection events. Now, this happens in a very short range of energy, actually, about factor 50 in energy, which means that only the very high energy particle close to the pulsar voltage manage to escape out of these systems. If I lower the energy even further, basically I get only few particles escaping out, nothing much. So in practice, these are filters. And that's the reason why we do not expect radio, because we expect essentially particles that escape out to have Lorentz factor of order 10 to the 6 or 10 to the 7. This is how jets came out. So you have an example of Geminga with the two hard tails. But de facto, depending on the systems that you can have essentially systems where you do have, for example, emission up ahead. This is the mouse, where you do see an halo sitting right on front of the A. This is the radio. So the radio is a clear bow shock, and there is X-ray emission coming from this region, which suggests indeed diffusing particle ahead of the shock. And for the final things, let's go. This is the pictures where you do see essentially the escaping strain. Now, the simulation cuts at the head. So what is the fate of these streams remain to be established. In the sense that you have particle streaming, we have an idea of what is the charge content and the particle number content out of this. Now, this system is typically 10 to the 17 centimeters. The tails is 10 parsecs. So now you have to do 2 orders of magnitude more in propagation. Now, to give you an idea of what propagation means for these systems, I will look at the point I cited before, so the presence essentially of bending in the structure. So the key idea is that now, once you emerge out, you are free streaming through the magnetic field lines, which means that somehow you are sampling the structure of the magnetic field in the ISM to 0th order, at least the large scale. And what you would expect is essentially that if the length is very short, below the coherent length of the magnetic field, you will actually sample a magnetic field that's mostly straight by definitions. So short tail should actually be straighters. If you go beyond the term parsec, you will start to sample the coherence of the magnetic field on scale that are comparable to. So you will start to see the bending of the ISM magnetic field. And so you would expect to see features that bend through. So the features that's seen here, for example, that has been interpreted as the presence of an helical jet that precess and things like that, could actually be simply due because the ISM in which you are moving has a magnetic field which typically bend on this scale. The question remains about the strength of the magnetic field, and the general idea is that if you have a charge-separated current, you can drive instability, resonant instability, in this, non-resonant instability in this case, and with non-resonant instability, you can amplify the magnetic field, which is also required because if you let particle free stream through, you would never reach the particle density that you need in order to explain the brightness of these features. The particle must somehow get stuck inside the system, so they do not propagate at the speed of light. And I'm concluding. So this is a typical example of a structure very similar to what happened to the solar wind, but in a very different regime. You have high energy particles. You do see the interaction with the ISM, and you do see from the outside. You have actually no idea what the wind is doing in. It's very difficult to sample the structure of the wind, but we do see its interaction. We do see its interaction both through the low-level radio and H-alpha, which gives you idea of how the ISM is impacting these systems, and through the production of high-energy particle and the escapes. Now, the escapes is quite important because ultimately you are putting out positrons, electrons at very high energy. So this makes these pulsars one of the greatest antimatter factor in the galaxy. So if you wonder why there is antimatter, there are plenty of pulsars around that are pushing antimatter through space. And the other issue is that these leptons will produce TeV halos and gamma ray emission. This is a particular concern for future gamma ray observatory because as of today, we only know of the Geminga halo and probably another couple of halos here and there. But in the future, with the CTA, we will be able to sample much deeper. So there will be a problem, so we will start to see plenty of these structure and these things. And it will be an issue to understand that because there's a big problems of gamma ray astronomy is to figure out what is, especially for extended source, what actually is a source and what is the background. Typically in the galaxy, the things are mixed up. So understanding exactly the level of backgrounds and how many of these sources will show up and how to correlate them with possible pulsar. Pulsar are all over, so the fact that you see a gamma ray source close by to a pulsar doesn't make the two are necessarily associated, but there is a higher chance than this. Okay, and I thank you. I don't know if I screwed up. No.
So the reconnection basically set up the conduit for your particle, for
Yeah.
your positron mechanism to come out. Why the
Sorry.
low energy electrons not coming out easily as the higher energy? Why you change by a factor of 50 is
Wait, okay, so, okay, let me go here. So the reason why they don't come out is that basically they need to get to the reconnection point. So the reconnection point is quite small in size. And if the particle managed to somehow get confined within the current sheet, and move there, once the current sheet reconnect, they manage to find their way out. Low energy particles have problems getting to the current sheet to begin with, because they are stuck to the bulk of plasma. So high energy particles manage to propagate, and when they enter the current sheet, start to mirror through and get confined. So if I go back in this picture, essentially, if I put low energy particles, I put them under shock, right? So the particle that I put it here, or here, and they have high energy, they manage to get to the current sheet somehow with a couple of Larmor radii. The one with the very small Larmor radii, before they arrive here, they will be flown back into the tail. And once they are pushed into the tail, they could reconnect, but much farther out. They will not contribute to these fishes that pops up from the head anymore.
If you were to make this assumption, if you have protons, then they have larger.
If you have protons, you could do that. Yes. So if you basically you are relativistic systems, it doesn't really matter what the mass of the particle. It matters what's the Larmor radius, or if you want the rigidity. So if you have protons which have I don't know, Lorentz factor which is 1,000 times smaller than electrons, that's fine. They will behave exactly the same way. They can escape.
Let us stop here. Thank you again.
Yeah.
So now from Paris to Torino, what he graduated here.
Okay. Can you hear me? Okay, great, thanks. Okay. So I wasn't expecting to be the closing speaker, but I guess what? I'm going full screen now. Yeah. Did it work? Okay, great. So thank you everyone for sticking around till this very moment. I'm Matteo Bugli. I'm a Marie Curie Fellow at the University of Turin. Previously, I was a postdoc in CEA-Saclay, just short of a few kilometers from Paris. What I will present you today is essentially the work I've been conducting in the past few years with the group of Thierry Foglisso and Jérôme Guillet at the Astrophysics department of CEA, focused on the modeling of Kirk-collapse supernovae, in particular connected to the formation of magnetars. So You heard already, I think, essentially from Nicola, something about the genesis and formation of compact objects and neutron stars. Essentially, what we are talking about is we start with the end life of a massive star, more than 8 solar masses, let's say, whose core becomes gravitationally unstable and start collapsing onto itself. And what we have is a scenario where the central densities of the star becomes rising. At some point, they will reach nuclear density values, 10 to the 14 grams per centimeters cubed. And once that occurs, essentially the material that keeps falling and that undergoes delocalization, and so we have a huge emission, a continuous emission of neutrinos that you can see with these light rays emitted from the dense core. At some point, the material will start bouncing on top of the hard core of what is now become a protoneutron star. So we have the formation of the shock, and essentially the shock starts expanding, but at some point it stalls. It stalls essentially because it doesn't have enough energy to propagate throughout all the layers of the star, and so it loses energy because of photodissociation and the run pressure of all the layers of the star, which keep falling on top of it. And so, in order to have a supernova, what we actually need is some sort of extra mechanism that energizes the shock and allows it to expand and to make the star go boom. So, in terms of energy budget, we start with a huge reservoir of gravitational binding energy, and almost the totality of it is actually emitted in the form of neutrinos throughout all the stages of the collapse. A tiny fraction of it, 1%, eventually gets stored into the ejecta, and a fraction of that is what we actually can observe through the electromagnetic radiation. An even tinier fraction, then, we do expect to be emitted in the form of gravitational waves. And what I will show you is that actually, despite this humongous difference in energetics between neutrinos and gravitational waves, they actually encode lots of the same information in the signal that we can possibly detect. So the so-called standard neutrino-driven core collapse supernova mechanism concerns the vast majority of core collapse supernovae. Essentially, the picture here shows the stalling shock, which is not completely spherical. The material starts falling. Here we have the heating up of the material, decrease in velocity. And here you see the protoneutron star, which is a very different beast from actual standard neutron stars. What we have here is an object which is very hot. It's an object that is convectively unstable. It's in inner zones between 10 and 15 and 25 kilometers. And beyond that, when we have rotation, it's actually differentially rotating. So it can be actually unstable to the magneto-rotational instability, the MRI. And the neutrino heating mechanism essentially relies on neutrinos, which are continuously emitted from the surface of the protoneutron star, to be, in a tiny fraction, actually absorbed just behind the shock. So when a fraction of the neutrinos doesn't freely stream away, but is actually absorbed in this region, we do have a heating mechanism that actually energizes the shock. We have the onset of convection, and hence a way to actually push forward the shock front. And in these scenarios, what we understood in the latest year is that multidimensional instabilities, fluid instabilities, are fundamental to actually allow and promote these mechanisms. So whether we talk about the convection behind the shock, or the SASI, which if you were listening to Nicola's talk, is the standing accretion shock instability. So all these dynamical effects actually contribute to make the neutrino mechanism very efficient in exploding the star. And so during these stages, there is no chance to actually take a peek at what is happening right at the core of the star. There is no, in terms of electromagnetic signals. But what we can rely on is the signals that we do expect in terms of both neutrinos and gravitational waves that occur just in a few milliseconds, 100 milliseconds after the formation of the shock. And that encode an incredible amount of information in terms of the dynamics of the protoneutron star. So this SASI, the standing accretion shock instability, is a major player in energizing the shock. Essentially, the core mechanism relies on the fact that we have essentially a resonant cavity between the shock and the surface of the protoneutron star, where we can actually close a cycle that involves the coupling of acoustic modes that are generated from the, emitted from the surface of the neutron star, and entropy or vorticity mode that actually are coming from the shock. So here you see the neutron star, which is essentially at some point is surrounded by the shock front, and you can see that it starts to wobble. It starts to turn around, and it's actually not at all stationary, and it's very non-asymmetric. And we do have lots of asymmetries, and these are fundamental when it comes to actually imprinting these asymmetries, for instance, in the kick velocity of the neutron star, in the explosion morphology, and it all comes down to this instability that occurs at this stage of the explosion. And you see here also the fact that it can induce a deformation in the neutron star. It can excite oscillation modes that are responsible for also the emission of gravitational waves at this stage. And if you see actually some water around the neutron star, this is not actually what we expect to find around the neutron star, but this is an example of an exact analog of the dynamics of the instability of the shock that can be reproduced within the framework of shallow waters. So this is effectively a fountain that is set up in such a way to actually reproduce this instability. It can reproduce the modes that we can just retrieve from a linear stability analysis. And this is something that has been done by Thierry Forizo and the team at CEA. And by the way, if you are intrigued by these animations in the movie, just go on YouTube and search for how does a supernova explode, and there is a wonderful video produced by the team, and it's just, it's amazing, really. So I had no part in it, so it's not to brag. Okay, so another example of instability that we actually expect to see in the presence of fast rotation in core-collapsed supernovae is a so-called low T over W instability. So T over W is the ratio between the rotational kinetic energy and the gravitational energy. And when I mean low, is that is just a few percent of this ratio. And this is low with respect, for instance, to the bar instability. Like if you're familiar with it, basically its onset is around 27%. But a few percent of this quantity means still a very fast progenitor. So here we're talking about a progenitor that is expected to produce a millisecond pulsar, proto-magnetar, for instance, if we have a strong magnetic field. And so this instability manifests itself with these large-scale modes and density perturbations that are typically m equal 1, but also m equal 2. This is the equatorial plane. And by decreasing the rotation, we actually decrease the coherence and the speed and the growth rate of the instability. And here in this diagram, you actually see the expected and associated gravitational wave signal. And this strong peak here is essentially due to this instability. So we have a very dense system with these extremely well-defined large-scale spirals that just keep turning. This is an exceptional source of gravitational waves. So what about magnetic fields now? So neutrinos are extremely efficient in explaining the vast majority of core-collapsed supernovae, but not really outstanding stellar explosions that present either very large kinetic energy with respect to the standard scenarios, such as hypernovae or gamma-ray burst, long gamma-ray burst, or exceptionally high luminosity, such as superluminous supernovae. So one way to address this problem is to consider both fast rotation and strong magnetic fields. The fast rotation provides an extra energy reservoir that can be tapped to energize further the explosion, whereas strong magnetic fields provide a way to tap into that by exerting magnetic braking, so slowing down the proton-neutron star, and then energizing the explosion, and produces, for instance, in 3D models, these outstanding bipolar explosions. So the question of the origin of the magnetic field, of course, is a very important one. It's something that for which we don't have a definite answer to. There are several proposed mechanisms. The one I will be focusing on is where we invoked dynamos that actually occur inside the proton-neutron star during the collapse and during the explosion. Because as you can remember, the proton-neutron star is convectively unstable, is differentially rotating, and this is essentially provides a natural way to invoke dynamos. And this is work that my colleagues at CEA have performed in the past few years. So they essentially have considered the action of the magnetorotational instability inside the proton-neutron star, or in the convectively unstable layers of the star as well. And they saw that there is effectively a very efficient mechanism in both these cases that can amplify the magnetic fields up to quasi-magnetary levels, so 10 to the 14, even 10 to the 15 Gauss. And the striking result is that these magnetic fields are in basically none of the case are very clean, for instance, the aligned dipolar field. They are highly multipolar, distributing on smaller scales, and they're highly misaligned with the rotational axis. So in many cases, actually, for the MRI cases, actually the majority of the dipolar field generated by the dynamo was actually equatorial, an equatorial dipole produced by that. And so the question is, how do this field actually impact the explosion? This was the driving question for the numerical models that I produced with the NOS-ALCAR code. So these are some specs. But essentially, I took a massive stellar progenitor, 35 zero-age main sequence solar masses, a huge hadron core of 2.1 solar masses, which has rapid rotation. And most importantly, we overlapped on top of it dipolar and quadrupolar magnetic fields, so different multiples, but also an equatorial dipolar field. Sorry. And we wanted to address the question, what happens to the efficiency of the magnetorotational explosion? So this is the hydrodynamic benchmark. You see, this is the surface of the proton-neutron star. And as the shock forms, you see the wobbling on the surface that is supposed to be associated with the emission of gravitational waves. These are the gravitationally bound ejecta color-coded by the specific entropy. And you can see that the explosion takes a while, so the shock is stalling, but it's being energized by the neutrinos, and at some point, the ejecta start to expand, and the explosion eventually takes place. It's not very spherical, very symmetric, far from it, but it doesn't really resemble those bipolar outflows that we saw for the magnetic case. And if we instead look at the case of the aligned dipolar field, what we see is actually something completely different. We have a prompt explosion of the ejecta. The magnetic flux is huge. The toroidal field amplified by the differential rotation really pumps the ejecta in the polar region, and we have these extremely axisymmetric bipolar outflows that just drills through the layers of the star. So this is a prototypical magnetorotational explosions. And when we consider the case of quadrupolar fields and the equatorial dipoles, essentially we have something that falls a little bit in between. We have explosions that are a bit less collimated for the quadrupolar field, and for the equatorial dipole, we have something sort of a hybrid where we have an external layer which is sort of spherical, symmetric, but an inner high entropy column that again drills through the star. So very different morphologies, very different energetics. The bipolar explosion is expanding much faster and much more energetic with respect to the hydro, which is at the very tail of it. But what we wanted to address in our most recent work is the onset of the low dynamic stability and the connection to the multi-messenger emission. So that's what we looked at. And on the left, you can see essentially the non-symmetric large-scale structures in density that I showed you before that are produced in our hydrodynamic benchmark. We see these beautiful two spiral arms being produced at roughly 200 milliseconds after bounce. And for the magnetized case, here I'm just showcasing the aligned dipolar case, model. There's no such thing. So the structures of the density are much smaller, and we don't have the clear onset of the low TOW instability. And if we take a look at the modes inside the proton-neutron star, so we're going 30 kilometers inside the proton neutron star. We calculate the spherical harmonic modes. This is on the left, the L equal 1, M equal 1, and on the right, L2, M2. And we trace a frequency time diagram of each of these modes. You can see here for the hydro case that there is a clear emergence of a clear mode at 200 milliseconds, exactly where the spirals are seen in these simulations. And the actual L equals 2 mode presents this sort of bizarre mirroring, which is just due to the aliasing. So we were not sampling the output with high frequency, a frequency high enough, and so we have this sort of mirroring. But if we did, we would actually see a signal that just goes ramping up at twice the frequency with respect to the one on the left. But if we look at the case of the model with a quadrupolar field, we still see these modes, but they are much weaker. And if we look at these white lines that represent the frequency, the rotational frequency inside the proton neutron star, so this, the lowest one is at the surface, and the highest one is at the center of the proton neutron star. So you see how narrow of a band we have for the quadrupolar field. And this represents the efficient transport of angular momentum for the magnetized case. So instead of having lots of differential rotation that translates into a wide range of frequencies, for the quadrupolar field, we have transport of angular momentum, a flattening of the rotational curve, and so a narrowing of this band. And this goes against the onset of the low TOVW, stabilizes against it, because low TOVW is essentially a co-rotational instability. It needs differential rotation and needs a co-rotation to occur. And so if we look at gravitational signal, we see what we expect actually from these results. We see a huge burst of gravitational waves in the hydro case at 300 milliseconds. And if we look at the spectrogram, we see this very nice mode rising that essentially matches the shape of the L equals 2 mode that we saw inside the proton neutron star. So this is the smoking gun of the dynamics inside the proton neutron star, just observed in gravitational waves. And for the magnetized case, once again, we do see a significant emission. It's not as clear, and it's actually broader band emission. So it's not just the rotational instability which is dominating, but actually there are either higher order modes or modes excited, for instance, by the MHD turbulence that occurs inside the proton neutron star that are responsible for the signal, which is an order of magnitude weaker than the one during the burst that we see for the hydro case. So last couple of slides, just to mention neutrinos. So I mentioned to you that there is actually a high degree of correlation between neutrinos and gravitational waves. And this is exactly what we see. In these 4 panels, we have the neutrino luminosities for the 3 species of neutrinos that we follow along the equatorial line of sight. So this is the hydro case, align dipole, equatorial dipole, and quadrupole. And what you can see right away is that the hydro case has the highest neutrino luminosities. And this is just due to the fact that it has less of a transport of angular momentum, which means that it has less rotational support in the external part of PNS. And so the PNS is actually more spherical. And the fact that in the magnetized case, we have a more oblate proton neutron star, that means that at the equator, the surface lies in a colder region of the surroundings of the PNS, and so the mean energies are lower, and the flux then are lower, and the luminosities are so lower. But if you look also carefully, you can detect these sort of high frequency oscillations that kick in exactly at 200 milliseconds. So this is another smoking gun for the low TOVW instability in the hydrodynamic case that we can find again, in this case with the L equal 1 mode, which cannot be seen in gravitational waves because they are inherently quadrupolar, but we see the L equal 1 and the L equal 2 also mode showing here. Whereas for the magnetized case, it's much less clear. So those modes might be contributing, but the onset of the low TOVW is definitely quenched by the action of magnetic fields. Last slide. This is essentially another signature, not for the low TOVW instability, but this time for SASI. So SASI is an instability that occurs at much lower frequencies than the rotational frequencies in the proton neutron star, typically between a few tens of hertz, up to 100 hertz. And essentially here I show the frequency time analysis on top for the surface of the shock for the 1-1 mode and 2-2 modes. You can see this feature here, which it's a little smurred because we had to, in order to have enough frequency resolution, we had to sort of increase the width of our window, and so that sort of ruins a bit the time resolution. But essentially, this feature is also seen in the neutrino emission. So again, the neutrino signal encodes extremely interesting and important information on the dynamics during the collapse and the explosion. Which, in this case, this was a magnetized model. So contrary to the low W, we can still have the development of SASI in the magnetized model that can actually leave an imprint signature in the signal. So this is my summary. In a nutshell, I showed you what we can do in terms of modeling of magnetized through the core collapse supernovae, and most importantly, what we can actually expect to observationally detect that can put important constraints on the dynamics of the proton neutron star. I didn't mention it, but we can actually tell a lot also about the properties of the proton neutron stars in terms of radius, in terms of mass, because there are other components of the gravitational wave signal that we can use to constrain them. The highest peaks in gravitational waves that we can expect come from the very fast rotating progenitors, which are also, unfortunately, much rarer than the regular core collapse supernovae. But even more, if we add magnetic fields that we do expect to be amplified by dynamos, that means that it's even less likely that this instability will thrive and deliver the signals. So, of course, I show a very small sample, and actually it's not very representative of the vast majority of the core collapse supernovae population. So, in order to tell something more about what occurs in the universe, we actually need to address lower rotational rates, weaker magnetic fields, tell something more about the low T over W, and this is something that I only briefly mentioned here, can have a huge impact when it comes to the details and the outcomes of the explosive nucleosynthesis that occurs in magnetic rotational explosions, which actually are still a candidate for the heavy R process elements that can pollute the galaxies and determine the chemical evolution of our universe. Just on a very quick note, I will just explain to you why I'm sporting this unusual, is for me, mustache. The reason for that is it's November, and November is the month of Movember. So if you're not familiar with it, you can check it out. Essentially, Movember is an event for charity where funds are raised to raise awareness, but most importantly, money for the research of prostate and testicular cancer. And so there are many ways to contribute. Men can grow a mustache from scratch, clean shaved up to the end of the month, and women can contribute as well, so can make a 60-kilometer run, and so on and so forth. So if you want to check my profile, make a donation, or just are curious of what this GIF will actually look like at the end of the month, just take a look at the QR code, and with this, I thank you for your attention. Yeah, indeed. Yeah, I agree. I think that, as Nicolas mentioned, the most likely explanation for the kick distribution of neutron stars and the correlation or anti-correlation with, for instance, the rotational axis of the ejecta is probably a combination of probably different mechanisms that might be responsible for that. But yeah, but it's cassé. Then it's just one. It's a sort of a poor statistical sample. Indeed. We're waiting for more. We're waiting for a galactic supernova. With that, it's going to be interesting. Yeah. Let's be. So I didn't have time to give a bit of more details about that. So in the community, there are actually groups relying on a full GR MHD codes coupled to a multidimensional M1 neutrino transport. So and these are the most expensive state-of-the-art simulations. Well, it's handled with a M1 closure. So we actually do have integrate the we have equation for the number density, the flux, and we have a closure for the energy, similar to what is done, for instance, also in GRMHD for the photon radiation in accretion disks. Essentially, is a sort of a moment closure approximation that is actually required. So the neutrinos for neutrino-driven corpuscular supernovae are essential because otherwise the star simply would not explode. The trade-off for that is that those models are so expensive that can actually follow the evolution of the supernova up to, let's say, a few hundred milliseconds, maybe 1 second if one has a humongous computational budget. The code that I've been using actually is adopting the alternative strategy, which is to start from a Newtonian description of gravity and then applying relativistic correction to the spherical component of the potential, a TOV sort of correction that takes into account relativistic effects, which has been shown to actually reproduce up to satisfactory quantitative agreement. For instance, the dynamics of the bounce and therefore after. So the trade-off is that you are not exactly as accurate as a full GR code, but then you can probe several seconds in 3D. And most importantly, you can also probe several models, for instance, for the same setup. And this is, for instance, what we've done. Another tricky part is the equation of state, which has to be taken into account. Nuclear densities matter for the particular neutron star, and lots of uncertainties there, but that is something that has to be taken into account and sometimes can give some troubles numerically. So magnetic fields can do that, but at very, very high intensity. I'm not sure. So we do reach 10 to the 15, in some cases 10 to the 16 Gauss inside the particular neutron star. As far as I know, it's still relatively safe in terms of dynamical impact on the equation of state for the particular neutron star, at least in this regime. But so as far as I know, there are at least the vast majority of the models that I know do not need to actually take that into account. How strong? Yeah, but how strong the magnetic fields? 10 to the 16 already. Okay. Okay. So 10 to the 16. Oh. Okay. Thank you.
Thanks again.